All right, hello everyone. Welcome to the second day of the Quantum Science Center's inaugural Quantum Summer School. I hope you all enjoyed the first day and ready for the second day. So first of all, let me start with introducing myself. This is Kübra Yeter Aydeniz. I'm a postdoc at Oak Ridge National Lab, and I will be moderating today's session. And today you will be hearing 3 great lectures from the experts in their fields, and that will be followed by hands-on activity after a half an hour break. So I would like to encourage you to post your questions to the Q&A box if you're on Zoom, or you can post it to the chat during the talk or at the end of the talk. And I will be reading those questions to Professor, and hopefully we will answer all of those questions. And if you are following us on YouTube, then you can post your questions to YouTube chat, and I will be reading those questions to the speaker as well. So without further ado, I would like to introduce the first speaker of the day. So Professor Jason Alicea, Professor of Theoretical Physics, Jason Alicea from California Institute of Technology is joining us today, and he will be talking about Majorana engineering challenges and opportunities. So welcome,
Thank you so
Professor
much,
Alicea. Please take it away.
Appreciate the introduction, and thank you all for having me at your school. So I'm going to tell you about the quest for intrinsically fault-tolerant quantum computing hardware based on something called Majorana zero modes. This subject is hard to do justice to in just a single-hour lecture, but I do have a few concrete goals that I'd like to get across. So first, I want to describe to you the basic theoretical underpinnings of what Majorana zero modes are and how they can be useful for quantum computing. Second, I'd like to give you a sense for where we are in terms of experiments and bringing this idea to life. And finally, if there's time, I'll try to give you a sense for what might be hopefully coming in the future of this field in the not too distant horizon. Can people see my pointer, by the way, if I use this as a pointer throughout? Is this visible?
I cannot see it right now.
Okay, that's too bad. So let me see if I can. Okay, do you know how I can, I think it'd be very useful for me to be able to highlight different parts of my slides.
You can go out of the full screen and try to turn on the laser pointer by right-clicking. Okay, now I can see your cursor.
Yeah, I'm gonna lose some. Okay, well, I'm just gonna continue. I'll do the best I can. Okay, so let me start the story by reminding you of the notion of exchange statistics and identical particles in quantum mechanics. So exchange statistics describes how wave functions transform when you have a set of identical quantum particles and swap their positions. So suppose that these red particles are some identical quantum particles described by some wave function psi. If you take a pair of these particles and swap their positions.
I'm sorry, I don't think the slides are moving along. Are you in the first slide or?
Okay, so let me, I don't know what to do. This is very funny. So why don't I stop sharing and I'll try it a different way.
Okay.
Okay, so do you see things now?
Yes, now it's good, moving perfect.
Okay, and can you see my cursor now?
Cursor, yes.
Okay, wonderful. Okay, great.
Perfect. Thank you.
All right, so I don't know how much this got across, but yeah, so suppose you have some set of identical quantum particles described by a wave function psi. The basic question is, if you take a pair of those particles and then swap their positions, how does that initial wave function evolve? And the relation between the initial and final wave function quantifies the exchange statistics for whatever particles you were dealing with. So this property is actually extraordinarily fundamental. Exchange statistics is one of the basic pillars of many particle quantum mechanics. and in fact underlies most condensed matter phenomena that we see in nature, ranging from the existence of insulators to metals, superfluids, superconductors, and on. So in terms of exchange statistics, nature allows for only a few different classes of particles. Two that we're all familiar with from beginning of our physics education are bosons and fermions. So for bosons and fermions, your wave function under a single exchange requires either plus sign for bosons or a minus sign for fermions. It turns out that for deep reasons, all elementary particles that our universe supports necessarily corresponds to one of these bosons or fermions. But interestingly, that does not quite exhaust the full set of possibilities that we have at our disposal. So in my view, one of the most remarkable manifestations of more is different is that you can take large collections of bosons and fermions, bring them together inside of a material, allow them to interact, and such systems can give birth to new kinds of emergent particles called anyons that have more interesting kinds of exchange statistics. Anyons can be further subdivided into two categories. The simpler variety are so-called abelian anyons. So for abelian anyons, if you swap two such particles, your wave function acquires a complex phase factor e to the I theta that's intermediate between plus or minus 1. So we call these abelian anyons because sequential exchanges commute. If you perform multiple exchanges of these kinds of particles, the wave function just acquires the sum of the phase factors associated with each individual exchange, and the order in which those exchanges were carried out makes no difference. Now, although this is already quite exotic, we nowadays know of many experimental platforms for abelian anyons. In fact, any of the many systems that host the fractional quantum Hall effect are almost certainly realize abelian anyons. And in fact, nowadays we even have direct experimental demonstrations of that kind of statistics. So my lecture today will focus on the second species of anyons, so-called non-abelian anyons, which are much more exotic and elusive objects compared to their abelian cousins. So non-abelian anyons can arise in certain kinds of topological phases of matter. And so for the sake of discussion, suppose that you have a phase of matter that supports these emergent particles. So let me describe the basic characteristics that these non-abelian anyons exhibit. So one interesting feature of these particles is that as you start to populate them into your system, the system acquires an exponentially growing ground state degeneracy. So for instance, if I nucleate a single pair of non-abelian anyons, your system might have not one, but two degenerate ground states to choose from. Nucleating a second pair grows the ground state degeneracy to 4. A third pair gives you 8 states, and so on. So you get this exponentially exploding set of ground states. Now, at this point, you might be intrigued, but perhaps not impressed, because ground state degeneracy by itself is not so extraordinary. In fact, I'll give you an example of a system that's completely trivial that has exactly the same kind of exponentially growing ground state degeneracy, namely a system that corresponds to an insulator, just a boring insulator that features a bunch of free spin-and-a-half moments. And by free spin-and-a-halves, I just mean a spin degree of freedom that energetically doesn't care whether it points up or down. So every time you introduce an extra free spin-and-a-half degree of freedom into such a system, you grow the ground state degeneracy by a factor of 2, precisely as I just showed you happens for non-abelian anyons. All right, so that's true, but I want to sharply contrast the kinds of ground state degeneracy that we get from this trivial system down here and from non-abelian anyons. Okay, so first of all, at least as a matter of principle, for these free spin-and-a-halves, you can perform local measurements to identify which of these ground states your system actually populates. So for example, you could imagine coming in and just locally measuring the magnetization associated with each of these spins and therefore reconstruct which of these states your system populated. In sharp contrast, that's fundamentally impossible in the case of non-abelian anyons. There are no local measurements that give you any information about which of these ground states your system is actually populating. A closely related property is that for these free spin-halves, this degeneracy is by no means robust. So you can easily lift that degeneracy either partially or completely by, for instance, applying magnetic fields that locally favor one spin orientation over the other. Again, in sharp contrast for these non-abelian anyons, there are this degeneracy is protected. There aren't any local perturbations that you can apply that destroys that degeneracy, whether those perturbations are magnetic fields, electric fields, disorder, and so on. So long as those perturbations are not so severe so as to destroy the topological phase of matter that allows these non-abelian anyons to form in the first place. Okay, so what we learned from this comparison is that anyons, these non-abelian anyons, must carry some kind of unusual zero energy degrees of freedom that are very different from spin flips, and instead generate a special kind of ground state degeneracy consisting of states that are all locally indistinguishable from each other. So that's the key property of non-abelian anyons. It's not just that they generate a ground state degeneracy, but they generate a set of ground states that you cannot distinguish via our arbitrary local measurements. So that's the first key feature of non-abelian anyons. So let's go a little bit further and imagine that by some means you initialize your system into one of those degenerate ground states, which I'll call psi sub I. All right, so then let's take a pair of these non-abelian anyons and then swap their positions and ask what happens. So although these are identical quantum particles, that exchange does something quite extraordinary. In particular, that exchange will fundamentally transform your system's quantum state. So more precisely, your initial quantum state will get non-trivially rotated within this ground state manifold, and that rotation will be quantified by a so-called braid matrix UIJ. So that's a remarkable phenomenon of non-abelian statistics. That's the most exotic kind of exchange statistics that nature allows us to find as a matter of principle. And so incidentally, the word non-abelian is attached here because in contrast to abelian anyons, order now matters. Basically because matrix multiplication is generally non-commutative, that implies that the final state that you end up in after some sequence of exchanges is very sensitive to the order in which those exchanges were carried out. So that's the second key feature of non-abelian anyons. The third is that they exhibit so-called non-trivial fusion rules. So this means that if you take two non-abelian anyons, bring them together in space, they can always combine to form at least two kinds of particles. And to put this property into perspective, you might consider as a reference, let's say electron and positron. If you take an electron and positron, bring them together, they're antiparticles of one another, and there's no question they will annihilate. In the case of these non-abelian anyons, there is never a unique answer. If you bring them together, they might annihilate, or they might form some completely different kind of non-trivial particle. All right, so these are the basic three pillars of non-abelian anyon DNA, if you like. They encode locally indistinguishable ground states, they obey non-abelian statistics, and exhibit non-trivial fusion rules. So this physics, I think, is quite beautiful on its own, and by itself warrants the pursuit of these kind of emergent particles in a laboratory setting. But quite amazingly, there are also technological applications for this remarkable physics. So in particular, as Alexei Kitaev taught us a number of years ago, you can in principle use non-abelian anyons to build scalable, intrinsically fault-tolerant topological quantum computing hardware that was intrinsically immune to errors at the level of your basic hardware components. So let me sketch the basic idea for how this might work. So first of all, this set of locally indistinguishable ground states is a very attractive place to encode quantum information. So if you have 8 states, for instance, you have enough Hilbert space to encode 3 qubits. And the key idea here is that the same property that makes it difficult for an observer to decipher which of these states are actually populated via local measurements also endows those qubits with intrinsic resilience against local environmental noise. So by using the subspace generated by non-abelian anyons, we have a by default way of storing quantum information in a secure fashion. So in addition, we also have access to an intrinsically fault-tolerant set of quantum gates that can be applied to these qubits by virtue of non-abelian statistics. So here the idea is that these braid matrices Uij can be thought of as quantum gates that rotate your qubits in exquisitely precise ways that you as a user control depending on which of these particles you swapped and in what order. So this is how ideally, in an ideal world, a quantum algorithm would actually take place via some sequence of prescribed braiding operations. Now, eventually, you want to read out the information after you've finished a computation. And to that end, one can use non-trivial fusion rules. Right, so the basic idea here is that by bringing these particles together and fusing them, you convert these locally indistinguishable ground states into locally distinguishable states that you can then read out by conventional means. And by deciphering whether those particles fuse to, let's say, A or B, particle A or B, that in turn gives you information about the state of your qubits that was otherwise hidden from you when all these non-abelian anyons were far apart from one another. All right, so that in a nutshell is a basic idea behind topological quantum computing. I often like to call this Alexei's $3 million idea because in fact he won $3 million for coming up with topological quantum computing as one of the inaugural winners of the Fundamental Physics Prize several years ago. So although Alexei already answered the $3 million question in this field, the $1 billion question remains open, which is how do you bring the, how do you build the hardware to bring this beautiful idea to experimental life? So maybe I can pause. I see there are a few questions in the Q&A box, so maybe this is a useful time to just pause and address things before I move to the next phase of my talk.
There was one question from the beginning that might be answered, but I will ask anyways. When you say sequential changes, do you mean essentially some kind of operation?
Yeah, by sequential changes, I mean, suppose that you want to do not just one braid, but many braids. So maybe I can first start by exchanging these particles, and then I can exchange these ones, and then these ones, and so on. You could imagine doing those exchanges in different order, and the final state that you end up in is sensitive to the order in which you carried out that same set of exchanges. So that's a non-abelian aspect to the exchange. Order matters. It's non-commutative by design.
Mm-hmm. Yes, so and the second question is, if there is no additional quantum number in non-abelian anyons, which can be measured, for example, contrary to spin, why would one care? And how one can be sure that there's something inside for these anyons?
Okay, so let me see if I can actually open the Q&A box and read that question myself. Okay. All right, so I think it's a huge virtue, first of all, that that you have this the space of states that you cannot distinguish by, let's say, associating different quantum numbers to those different states. So that's that's what makes this whole idea of practical relevance for quantum computation. And the upshot is that suppose that you did have some quantum numbers that you could use to distinguish these states. For instance, maybe they had different energies. This is kind of not an ideal situation to find yourself in from the point of view of quantum information, because random fluctuations from the environment can cause, for instance, the energy difference between those states to fluctuate as a function of time. Mm-hmm. And those random fluctuations are in turn what can cause dephasing processes that are destructive to the quantum information. And so by intentionally stripping those states of locally distinguishable quantum numbers, you hide that quantum information from those kind of deleterious effects from the environment. So I hope that addresses that question.
Yeah, actually, there's one more question. Are there any relation between non-abelian anyons and the quark with flavors?
I think the short answer is no. In fact, quarks I would classify as the category of elementary particles. Elementary particles can never exhibit the phenomena of non-abelian statistics. This can only arise from conglomeration of many conventional elementary particles. And that has to do with the three-dimensional nature of our universe, essentially, which constrains particle exchange statistics and the elementary particle world to bosons or fermions.
Yeah. So another question is, what's the method being considered to bring two of these particles close, considering they are non-local?
Okay, so this is actually a kind of subtle point. So you can actually stabilize and trap non-abelian anyons via local perturbations. And so you can have local control about where they sit, but that does not mean that you can actually tell which state your system is populating from local measurements. So it's a little bit of a nuanced thing, and I think as I go a little bit further, you hopefully get a little bit more intuition for how these things can actually be controlled and synthesized in a practical laboratory setting.
Okay, I think these are all questions so far. So.
Okay, fantastic. Well, thank you for those questions, and keep them coming. I'll try to pause periodically as I go. All right, so at this point, this is the $1 billion question that we need to address. How do you bring this idea to life. And so what I'd like to do now is sketch some of the key milestones that have taken place in the pursuit of non-abelian anyons, starting from their inception and going to present day. So this whole idea of non-abelian anyons as a theoretical possibility originated in the late 1980s within the mathematical physics community. So people like Moore, Seiberg, Witten, and others were responsible for the birth of non-abelian anyons. Again, it's just as a theoretical possibility. But in those early days, there was absolutely no experimental connection. This was very much a pie in the sky idea. So the situation changed in 1991, which is the beginning of what I'll call the realizations era of this problem. In 1991, Moore and Reed made the pioneering advance by proposing that certain kinds of fractional quantum Hall states can naturally harbor non-abelian anyons. And 3 decades later, actually, this remains a viable pathway toward non-abelian anyon physics in the laboratory. Around 10 years after that, there were 2 seminal advances, one due to Reed and Green and another due to Kitaev, that showed that the essential non-abelian content of this non-trivial, strongly interacting non-abelian quantum Hall state could be distilled down to the realm of weakly correlated systems, namely certain kinds of topological superconductors, either in 2 dimensions or 1 dimension. So it's really hard to overemphasize how important this distillation from strong correlation to weak correlation actually was. And in fact, much of the progress in this field that's taken place over the last 10, 15 years has its roots in this critical observation. Now, despite the fact that these 2 works distilled non-abelian anyon physics into the weakly correlated realm, it took quite some time to figure out how you can actually make these kind of topological superconductors in a real world laboratory setting. Right, so it took about another 10 years to figure out how to do that. And eventually we entered what I'll call the design era beginning in 2008. Okay, so the first key breakthrough here came from Fu and Kane, who realized that you can actually engineer the physics of those topological superconductors by combining topological insulators and conventional garden variety superconductors. A couple of years later, there was another key development by Luchin et al. And Oreg et al., who distilled this idea even further by showing that you didn't even need topological materials at all. You could instead engineer topological superconductivity by combining semiconductor nanowires with ordinary superconductors. So by now, there are many variations, probably of order 100 different variations on this theme, which really translated these toy models for topological superconductors introduced in the early days into plausible experimental blueprints for how you could actually make them. That in turn gave way to what I'll call the fabrication and characterization era that began in 2012. So these kinds of proposals stimulated lots of experimental activity. People got very good at making some of these kinds of devices, started making measurements, characterizing them, and some of those measurements even gave hints that non-abelian anyon physics was forming in those structures. So this is where we more or less are at present. We're still in this fabrication and characterization era, at least in my view, and I think probably the majority of people's view in this problem. And so looking a little bit forward into the future, hopefully not too far forward, hopefully we will be soon entering the control era, where the emphasis will be less on device fabrication and characterization and more on controlling and manipulating non-abelian anyons to demonstrate all of the interesting non-abelian anyon characteristics that I showed you previously, and working our way up towards quantum computing applications. Okay, so this is more or less an outline for what I'd like to convey in the rest of my lecture. So what I'd like to do now is go back up and show you how, in the context of toy models for one-dimensional topological superconductors, how non-abelian anyon physics can arise in actually, I think, very intuitive settings. Then I'll show you how those toy models can actually be realized in nanowire-based devices, and say a little bit about experiments and future directions. Okay, so I see 4 more questions, so I don't know if I should pause and take those at this point, or no, so those are the same questions. Okay.
Yeah, there's more,
right.
more questions.
Fantastic. Okay, so let's now consider a toy model for a spinless one-dimensional superconductor, which, as we'll see shortly, can realize a topological phase that harbors non-abelian anyon physics. So here's a basic setup. I'd like to consider an n-site chain. So here's site 1, 2, 3, down to n. Spinless fermions will live in that n-site chain and will be governed by the Hamiltonian shown here. All right, so the spinless fermions will be described by operators C and C dagger. I'll give those spinless fermions a chemical potential, which allows us to fix the density in that system. Those spinless fermions can hop between nearest neighbor sites of the chain with hopping amplitude T. And if two fermions happen to sit at neighboring sites, they can form Cooper pairs with an amplitude delta. Okay, so that's the model that I'd like to consider. Now, as is often the case in condensed matter physics, the key to uncovering the physics of this Hamiltonian involves choosing the right degrees of freedom, the right set of variables to work with. So in this context, the right set of variables to work with turn out to be something called Majorana fermions. Okay, so I'm now going to take my original spinless fermion operators denoted by C and decompose them in terms of Majorana fermions by writing C as gamma B plus I gamma A. So gamma B and gamma A, those are so-called Majorana fermion operators. They satisfy the properties shown here. They square to 1, they're Hermitian, and they have fermionic anti-commutation relations with each other. So this is something that one can formally always do. There's nothing special about this particular model. This is always a legitimate way of writing any fermion operator. And it's really akin to just taking a complex number and writing it in terms of its real and imaginary parts. I think that's a pretty useful analogy. Okay, so just the fact that one can introduce such a decomposition on a formal level is often not very useful. And just because I decided to write things in terms of Majorana fermions doesn't mean that my system has excitations that are in any way related to Majorana fermions. But in this particular example, if you tune this Hamiltonian to a very special limit and use this Majorana fermion decomposition, the physics just jumps right out at you. So let me do that. Let me fine-tune this model to a very special point where the chemical potential vanishes and the hopping and pairing amplitudes equal each other. Okay, so this term is now gone, and T is equal to delta for these terms over here. And in this particular limit, I can factorize these remaining terms in a very nice way. Okay, so that Hamiltonian in the limit where mu is 0 and T equals delta can be expressed as shown here. So I've pulled out an overall energy scale T all the way out front. And I've factorized the remaining terms as shown here. Right, so to make sure that I haven't done anything wrong, you can kind of go in reverse and make sure that this Hamiltonian indeed recovers to the one I started with. So if you multiply these terms together, Cx dagger Cx plus 1, that's exactly this hopping term. If you multiply these terms together, that's exactly this pairing term. And then this Cx dagger piece just gives you the Hermitian conjugate terms. All right, so by staring at this particular form of the Hamiltonian, you can see that this first piece just involves Cx plus Cx dagger. So you can think about that roughly as the real part of this fermion, which will be related to gamma B. So that real part at site X will couple to the imaginary part C minus C dagger at the next site over, and that imaginary part is basically the gamma A fermion. All right, so when you introduce the Majorana fermion decomposition, this has a very nice representation. Here it is. The Hamiltonian reduces to the form shown here, which just couples gamma B at site X with gamma A at the next site over. All right, so here's a pictorial representation of that Hamiltonian. So here are the gamma A and gamma B fermions associated with site 1. Here are the gamma A and gamma B fermions associated with site 2. Here are those guys for site 3, and so on down the chain. All right, so this Hamiltonian will couple gamma B at site 1 with gamma A at site 2. They'll couple gamma B at site 2 with gamma A at site 3, gamma B at site 3 with gamma A at site 4, and so on down the chain. All right, so if you look in the bulk of the chain, in the interior of the chain, every Majorana fermion is coupled to one of its nearest neighbors. And those couplings turn out to create a finite energy gap everywhere in the chain. Right, so this is maybe not obvious, but one can show this in a couple of lines of algebra. But at the end, you can see that something very special has happened. So there's one Majorana fermion gamma A1 on the far left end, and a second Majorana fermion gamma Bn at the right end that's not coupled to anything. Okay, so those two Majorana fermion operators are explicitly absent from the Hamiltonian. They don't appear in the Hamiltonian. And therefore, they trivially commute with the Hamiltonian and are associated with 0 energy degrees of freedom. So I will call these unpaired Majorana zero modes. So the 0 aspect refers to the fact that they don't, you can act one of these operators on a given quantum state and you don't change its energy because those gammas commute with the Hamiltonian. Okay, so they're unpaired Majorana zero modes, unpaired because they're not coupled to any partner contrary to the ones in the interior. Okay, so usually I'll drop the unpaired and just call these things Majorana zero modes. All right, so these Majorana zero modes are the simplest kind of exotic 0 energy degree of freedom that I mentioned gets tethered to non-abelian anyons in my introductory slides. And in fact, those Majorana zero modes are the engine of all the interesting non-abelian enyon physics that we saw previously. So this might be another useful place for me to pause briefly. Are there any questions about this toy model? I'd be happy to answer them.
I don't see any other questions so far.
All right, well, please keep them coming. I'm happy to pause whenever it's useful. Okay, so let me now kind of zoom out a bit and describe how these Majorana zero modes can allow us to understand in a more intuitive and concrete setting all the interesting non-abelian enyon physics that I described to you previously. So this will be my more minimalist picture of one of these topological superconductors that we just captured on the previous slide. So this blue line, that's going to represent the bulk of our spinless one-dimensional superconductor that's fully gapped. And we'll have a pair of Majorana zero modes, one at the left end, one at the right end. And I'm going to describe those, just call those Majorana zero mode operators gamma 1 and gamma 2. Okay, so previously, remember that I was able to take our spinless fermion operators and decompose them in terms of a pair of Majorana fermions. We can similarly kind of go in reverse. So I have two Majorana zero mode operators, gamma 1 and gamma 2. And from those two operators, we can define a single spinless fermion F by superimposing gamma 1 plus I gamma 2. So that F level has a well-defined occupation number 0 or 1. And because these zero mode operators, by definition, commute with the Hamiltonian, this F operator also commutes with the Hamiltonian. Okay, so in other words, you can add or remove a fermion from that level without changing the system's energy, and therefore the system acquires a ground state degeneracy. So those two ground states are associated with occupation number 0 and 1 for that complex fermion F. And those ground states, as is one of the hallmarks of non-abelian anyons, are locally indistinguishable from one another. So we can understand that local indistinguishability in a variety of ways. First, we can note that fermion F arises from a superposition of two Majorana zero mode operators that can be separated by macroscopic distances from one another. And so if you want to know the occupation number of that fermion, you have to do a non-local measurement that simultaneously knows not just about gamma 1, but also about gamma 2. All right, so that's kind of a formal way of thinking about the problem. But there's a more physical way of thinking about this as well. So those two ground states that are, again, associated with occupation number 0 and 1 for that F fermionic level have correspond to states that have overall even number of fermions spread out across that superconductor, and a second state that has total odd number of fermions spread out across that superconductor. Now, interestingly, this is already a pretty bizarre feature. In conventional superconductors, the ground state typically has an even number of electrons so that every electron can find a partner to Cooper pair with. And typically, if you want to have an odd number of electrons, you have to have one unpaired fermion, and that will, in most superconductors, cost you a finite energy. So that energetic distinction between even and odd electron number ceases to exist in this setting, and that's the physics that these Majorana zero modes are encoding. Now, if you wanted to know whether your system had an even versus odd number of electrons, you would have to do something which is highly non-trivial. You would have to count up the total number of electrons in your delocalized across your system, mod by 2, and then you'd know whether you had an even or odd number of electrons. And clearly that's not information that you can get by just locally probing any given patch of the system. All right, so that's, I hope, makes the local indistinguishability a little bit more intuitively accessible. I also mentioned previously that as we nucleate these non-abelian anyons, we get exponentially exploding ground state degeneracy. And we can see that possibility here as well. So there's no reason why I need to just generate a single topological superconductor along this line. So you could imagine that, for instance, in the central region, I just remove all the electrons from that part of the system so that this just becomes some trivial vacuum, in which case I've essentially sliced that single topological superconductor in two. So I'd have one topological superconductor on the left, one topological superconductor on the right. Each one will have its own pair of Majorana zero mode operators. And so instead of having just two ground states, now I'd have four ground states. And those four ground states reflect the fact that each one of these segments can have even or odd electron number independently without changing the system's energy. I can continue. I could, if I want, put some electrons back in the central region, creating another topological superconductor, giving a third pair of Majorana zero modes, and growing the ground state degeneracy to 8. Okay, and you can keep doing this if you like and get as many of these states that as can fit in your sample. Okay, so that's local indistinguishability and exponentially growing ground states. Let's turn now to fusion. So I mentioned that if I take a pair of non-abelian anyons and bring them together, they can fuse two different kinds of quasi-particles. So we can see this property intuitively as well. So suppose now that I took this central region and moved these Majorana zero modes together so that I eventually just destroyed that central topological superconductor. All right, so it makes some logical sense that once I've removed that central region, I had better get back to having 4 ground states rather than 8, and which implies that the 8-fold ground state degeneracy had better split into a lower quartet and an upper quartet, which are no longer degenerate. Now, if you started in a state that evolved into this lower quartet, then those non-abelian anyons would have just annihilated with one another, and they're gone without a trace. However, if you ended up in this upper quartet, then you would be left with an extra finite energy fermion present in this region, which is the second possible channel that these non-abelian anyons can fuse into. And so another way of thinking about this is you can construct a fermion operator by writing gamma 5 plus I gamma 6. Once those two zero mode operators come together, they no longer commute with the Hamiltonian. It then costs you a finite energy to populate that fermionic level. And the two occupation numbers for that fermionic level correspond to the two different ways in which those non-abelian anyons can fuse. Either they can annihilate each other or give you an extra finite energy fermion. Okay, so that's fusion. Finally, I mentioned non-abelian statistics.
If you don't mind.
Yes, sure, yes, please go ahead.
Yeah, so is there an operator or a measurement that can tell you how many free Majorana zero modes are there in your system?
There is a measurement that can do that, and I will describe that actually later on. So maybe just let me pause on that. But in a nutshell, possibly you could use transport probes to reveal the presence of Majorana zero modes. You can't get you can't infer the state encoded by those Majorana zero modes, but at least the presence of a Majorana zero mode can be inferred by local transport measurements. So stay tuned, and I'll say a little bit more about that shortly.
Okay, thank you. Okay,
yeah, thank you for the question. So finally, let me mention non-abelian statistics. So if you, by some means, swap, let's say, gamma 3 and gamma 4, then you will find that your system gets rotated within that set of degenerate ground states, and that's the essence of non-abelian statistics. To get some intuition for this remarkable property, what you're really doing if you swap two pairs of Majorana zero modes is that you're essentially swapping half of one fermion with half of a different fermion, and that kind of naturally is going to readjust your states in a non-trivial way. And up to a minus sign, that's really the heart of non-abelian statistics. So I've shown you this in a very cartoonish way, but let me just assure you that there are concrete devices that one can at least envision making in the laboratory that allow you to do well-defined exchanges of Majorana zero modes in wire networks and other kind of geometries. Okay, so I hope that this gives you a flavor for how non-abelian anyon physics can arise. I think it's actually quite amazing that all of this physics can be distilled down to these kind of toy models that one can, almost solve at a level of homework problems. Now, unfortunately, making those toy models in the lab is not so easy. And there's three basic challenges involved with trying to create a spinless one-dimensional superconductor. So the first is kind of obvious challenge. We live in 3 dimensions. And so if you want to build this kind of superconductor, you have to fabricate artificially reduced dimensional channels for your fermions. This is not such a big deal. This is done all the time, but it does limit the materials options that we have to work with. Second and more non-trivial thing is that electrons, for better or worse, carry spin. So if you look at the energy versus momentum relation for typical materials, usually you find spin degenerate bands. And so in the ground state, the system will populate both spin up and spin down bands. And so in no sense will the system appear spinless. So if you want to make something that mimics spinless fermions, then you have to basically kick out one of those spin branches so you have one partially occupied band rather than 2. So the third challenge is that among the thousands of known superconducting materials that we have at our disposal nowadays, in almost every single one, superconductivity arises from the formation of spin singlet Cooper pairs. In other words, both spin up and spin down are essential for superconductivity in nearly all known cases. And there's obviously some tension between seeking a system that appears spinless and getting superconductivity in the first place. All right, so these are the 3 challenges that we have to confront in order to fabricate a topological superconductor with Majorana Azure modes in a laboratory setting. All right, so the good news is that we don't have to get lucky in this process. We now have a variety of ways of engineering these kinds of topological superconductors by judiciously combining ingredients that are already well understood on their own. So now I'm going to describe to you one of many proposals that have been put forth along these lines. So this is a pair of particularly influential works by Luchin et al. And Oreg et al. That appeared in PRL in 2010. So these authors provided a very appealing recipe for engineering Majorana Azure modes using one-dimensional spin orbit coupled wires, for instance, materials like indium arsenide, indium antimonide, and so on. To illustrate how this proposal works, let's start by thinking about the band structure for such a wire without spin orbit coupling. So without spin orbit coupling, if you look at the energy versus momentum for that wire, you get something like what I just showed you on the last slide, just a pair of spin degenerate parabolas. Right, so we are not even close to spinless yet. So let's now turn on spin orbit coupling. So once you turn on spin orbit coupling, you lift the spin degeneracy. And for instance, the spin up parabola can shift rightwards. The spin down parabola can shift leftwards. And so degeneracy has been mostly removed. But nevertheless, you can see that it's still not quite what we want, because it doesn't matter where you put your Fermi level here, you'll still be partially occupying both of those spin branches. Whereas I want to make the system look spinless, I want to have only a single partially occupied band. So the beauty of this setup is that this problem is very easy to cure. If you stare at this band structure, so there's a crossing at 0 momentum. And that crossing at 0 momentum is basically guaranteed by Cramer's theorem due to the presence of time reversal symmetry. And so by simply breaking time reversal symmetry, you can get rid of that crossing. And this can be easily done by just applying a magnetic field to the system. All right, so once you do away with that crossing, you can see that we're now in business, because if your Fermi level happens to sit inside of that field-induced gap, then you just have a single partially occupied band rather than 2. And in this important sense, your system now looks like it could be described by spinless fermions. Crucially, however, this has been done in a very smart way, because if you look at the states at the right Fermi point here, those states will be mostly pointing up. Their spins will mostly be pointing up, with their spin orientation weakly canted by this magnetic field. Similarly, on the left side, because of spin orbit coupling, these states will be mostly pointing down. The spins will mostly be pointing down, again, weakly canted by the magnetic field. Right? And so the fact that you have both spin up and spin down states available at the Fermi energy makes the system very easy, at least in principle, to make superconducting. Right? So this can be done by now coupling our spin orbit coupled wire to garden variety spin singlet superconductor, so one of the thousands of conventional superconductors that we have at our disposal. The key idea here is that electrons from this wire can tunnel into that superconductor and then back. And by spending a little bit of time in that adjacent region, those wire electrons can inherit properties that are native to that superconducting system. Okay, so that's a very powerful and useful phenomenon known as the proximity effect. So most importantly here, those electrons will soak up from some of that spin singlet superconductivity. And that spin singlet superconductivity can form very efficiently, once again, because we have both spin up and spin down states available at the Fermi energy to form spin singlet Cooper pairs. All right, so as long as your Fermi energy sits in the sweet spot, you will have driven your system into a one-dimensional topological superconducting phase that has a Majorana mode, one Majorana zero mode at each end of the wire. Given the simplicity of the ingredients that underlie this proposal, many experiments naturally followed in reasonably short order. Here's a pair of devices, one from the Delft group, one from the Copenhagen group, but there are many, many more from groups all around the world that have been fabricated in the last decade. All right, so next question I would like to ask is, once you have made such a device, what do you actually do experimentally to check whether you have made what you hope you have made? Okay, so let me, it looks like there's another question.
Yeah, there's one more question. So you showed that lift of the degeneracy. So is the degeneracy lifted due to fusion between the central Majoranas, or then they exactly at zero energy? Yeah, so the degeneracy will indeed be lifted once once these Majorana modes hybridize with each other. Then they will not be at exactly zero energy anymore. They'll be pushed to finite energy. And this is, that's the conversion of locally indistinguishable information to locally distinguishable information. Basically, now there's something that some local information that you can try to latch onto to distinguish the states that were otherwise degenerate and hidden from you when the zero modes were far apart. Okay, thank you. Okay, so I hope that answers that question. All right, so what I'd like to do next is actually to address one of the questions that was raised previously. How do you know if you've actually created a Majorana zero mode in your system? And so I will describe the dominant experimental scheme that's attempted to address that question, which uses local transport probes. Right, so it's a little bit of a nuanced thing. So via a local measurement, you can detect the existence of a Majorana zero mode, basically because there's a zero energy degree of freedom that you can try to probe. However, you can't, via local measurement, tell which state your system is populating. So there's no contradiction with things that I said earlier. All right, so let's see how you can try to detect the presence of Majorana zero modes via transport experiments. So let me now consider the geometry shown here. So I have a wire, which is this blue region. Half of that wire sits on top of a spin singlet superconductor. And I'm going to assume that the proximity effect gaps out this adjacent part of the wire. Right, so it doesn't necessarily need to be a topological superconducting phase with Majorana zero modes. It could be a trivial state as well, but I want to assume throughout this discussion that this region of the system is fully gapped. On the left side, our wire will just sit on top of an insulator, and so this part of the wire will remain gapless. And I'm going to treat that gapless part of the wire as a lead that will try to inject electrons onto this gap side of the system. And we'll see what we'll try to get some information from the conductance of this device as to what kind of superconducting state is formed on the right. Okay, so let me say that in a little bit more clearly. Sorry, was there a question? We have 10 minutes.
10 minutes, okay, perfect. Yeah, thanks. I think I'm in good shape time-wise. Perfect. All right, so more precisely, so imagine that you ground this superconductor and you hold this gapless part of the lead at a bias voltage V. So that bias voltage will try to send electric charge towards this superconducting region. And basically, by understanding the conductance that describes current flow from source to drain, we can try to get a lot of useful information about what's going on in this part of the system. Okay, so let's think about the kind of processes that can take place when an electron makes its way from the source towards this gapped region. All right, so that electron, because this region is gapped, can actually never enter the superconductor. And so the kind of processes that can arise are rather restricted. Okay, so one thing that can always arise is that an electron incident on that gapped region can just reflect back to you as an electron. That's what I'll call a normal reflection process. And since no charge has been injected to the superconductor, these normal reflection processes don't contribute to the current and don't contribute to the conductance. Now, interestingly, that's not the only kind of process that can arise. There's a second kind of process called Andreev reflection that's unique to superconductors. Okay, so in an Andreev reflection process, and something a little different happens, the incident electron bounces back to us, not as an electron, but rather as a hole, in turn injecting a Cooper pair into the superconductor. And the superconductor happily absorbs Cooper pairs because the superconductor is made out of a common state of Cooper pairs. So this Andreev reflection process will indeed contribute to the current and therefore to the conductance of this device. And more quantitatively, the conductance will be given by the conductance quantum E squared over H times the Andreev reflection probability with an extra factor of 2. And this extra factor of 2 basically is present because every time you have an Andreev reflection event, you inject not 1, but 2 electrons into the superconductor. All right, so I'm going to focus on the behavior of this conductance in the limit where all the energy scales are basically going to 0, and the limit where temperature goes to 0 and bias voltage goes to 0, because in that low energy scale limit, the behavior of this conductance becomes universal. And will depend, as I'll say in a moment, very sensitively on the kind of superconducting state that you've synthesized on the right-hand side of the system. So if you don't have any, if you just made a trivial superconductor, if you don't have any Majorana zero modes in this right part of the system, then it turns out that you get, with unit probability, normal reflection at low energies, an incident electron just bounces back to you as an electron, and the corresponding conductance will just vanish. In sharp contrast, if you've made what you hope to have made and have Majorana zero modes at the opposite ends of your wire, this Majorana zero mode hybridizes with your lead and qualitatively changes the outcome of this transport experiment. In particular, here, an incident electron with unit probability will Andreev reflect and bounce back as a whole, giving a pair of electrons that go to the drain. And the corresponding conductance in this case will be non-trivially quantized to 2 E squared over H. So this is a very appealing conductance dichotomy. What you might hope is to monitor the conductance at small bias voltages and small temperatures. And as you make your way from a trivial to a topological superconductor, you would try to look for this jump in the zero bias conductance, ideally from 0 to 2 E squared over H. This experiment has been done by many groups there's a large number of papers on this topic, both theoretically and both in theory and experiment. I'll just show you one example of a device from the Copenhagen group. Here's this is some of their measurements. So the color represents the conductance as a function of source drain bias voltage on the vertical axis and magnetic field along the horizontal axis. If you start at 0 magnetic field here, then you have no chance of getting Majorana zero modes, at least in this setting. You haven't yet opened up your spinless regime. And accordingly, the conductance is very small, very close to 0. As you crank up the magnetic field, you start to give yourself a chance of realizing a topological superconducting phase. And indeed, one sees in this measurement and in a variety of other measurements, zero bias peaks that form and stick around over some extended region of magnetic field. So nowadays, these experiments, while in some cases they can be consistent with the formation of Majorana zero modes, they're widely viewed as inconclusive and not quite definitive signatures of Majorana zero modes. And here's the basic culprit. There's a very simple picture that has emerged for why this is inconclusive. Essentially, turns out it's very hard to distinguish via this kind of transport measurement from a situation that we want, where you have Majorana zero modes separated across the length of your device, from a situation where you have a pair of weakly hybridized Majorana modes that just happen to sit close to your lead. Now, you might think that this sounds like a preposterous situation, but sadly, these weakly hybridized Majorana modes that are masquerading as true protected Majorana zero modes can arise quite naturally due to some combination of disorder and chemical potential variations that can naturally arise as you make your way from the interior of your sample to the boundary. So this is one of the key challenges that the field is wrestling with. We need to figure out how to get to more decisive signatures of Majorana zero modes to rule out this boring accidental low energy mode scenario. All right, so with this, I wanted to zoom out a bit and try to give you some sense for what I think are some interesting directions on the horizon of this problem. So here's the this Majorana mountain that I showed you in my title slide. Ideally, we'd like to eventually get to using these kind of Majorana devices for fault-tolerant, scalable quantum computing hardware. There's been a lot of exciting progress in this direction, but we certainly have, lots of ground to cover. So some of the exciting progress has involved the synthesis of toy models that allow us to understand in really simple and appealing, intuitive ways how non-abelian anyons can form. We've had a lot of progress in translating those toy models into concrete experimental blueprints, which in turn have inspired a lot of progress on the device fabrication front. And there's been a lot of activity on trying to detect Majorana zero modes in such devices, but there's a very dim check mark here because those experiments are largely remain inconclusive, at least in this nanowire kind of game that I've focused on here. Now, there's one other thing that I wanted to mention that's in the category of fabrication and characterization milestones, and that's the detection of a topological phase transition. I think this is actually a really useful thing to set one's sights on, both experimentally and theoretically. I didn't really emphasize this, but as you make your way from a trivial to a topological superconductor, those are distinct phases of matter and are separated by a phase transition at which the gap for the system closes and then reopens. And if you can see that closure and reopening, along with the corresponding formation of Majorana zero modes, I think that would provide very clear-cut experimental evidence of Majorana zero modes, even if you're just using the standard transport experiment that I described on the previous slide. Another thing I wanted to mention is that I think it's still very interesting to think about new experimental blueprints. A few years ago, I didn't think this was such an interesting problem anymore, but I've definitely changed my tune. I think there's still a lot of room to use the new condensed matter phenomena that are all the time being discovered and try to find new platforms that can give us non-abelian anyon physics. And I think the ideal platform is still not clear. Further up the mountain, I'm really excited about eventually getting to control era type milestones where we're capturing the essential non-abelian anyon physics, fusion role detection, non-abelian statistics, validating prototype topological qubits. I've spent a lot of my time in the last couple of years thinking about this, and I'm very excited to finally get there, hopefully not too much longer. Once we understand once we have all these control era milestones in place, we can think about multi-qubit devices, and there's a whole new set of interesting problems involving analog quantum simulation with Majorana arrays and device characterization as we work our way up towards the ultimate goal, which is to actually make a useful technology. The final thing I wanted to mention is that despite the fact that I've really focused on one route in this talk, there's by no means a unique path up this mountain. There are other trajectories that are being thought about, and here's some snapshot of some of them. And I think it's a really exciting problem, despite the fact that we've been struggling a bit to get truly decisive Majorana zero mode signatures. I think the discovery of all these other routes has given a lot of interesting fodder for this field. And so in conclusion, I hope that you all find this direction interesting, and I hope some of you will be inspired to help us trek up this mountain in the years to come. So thank you for your attention, and if I have any more time, I will be happy to answer more questions.
Thank you, Professor Alicea, for this great talk. We have some questions for the last 2 minutes that I can ask. So you showed this potential versus magnetic field plot. So is the superconductor destroyed when the magnetic field exceeds 200?
Okay, so I'm actually very happy to have gotten this question because, well, okay, so the superconductor is not destroyed at this field. It may be, you can see the superconductivity being destroyed maybe around a few hundred millitesla. But I do think that this is a very something that I'd like to comment on, and this is concerns how we might try to improve on these kind of proposals in the future. And one theme that has emerged in certain parts of the literature recently is trying to do away with the requirement of having a magnetic field in the first place. So magnetic fields and superconductors are usually not very close friends. And so if you can figure out a different way of breaking time reversal symmetry that leads to the same result, that's a step in the right direction. And concerning alternate pathways up the mountain, I think this is a very useful thing to keep in mind.
Yeah, so on the same plot, so it seems like G is only 0.8 of E squared over H instead of 2. Is a comment in that plot for that.
Yeah, so that's right. And the vast majority of these zero bias peaks have been below this 2E squared over H quantized value. That can be for a variety of reasons. It could be that one simply hasn't probed a Majorana zero mode and is probing something else. It could be even in the scenario where you do have a Majorana zero mode, this could be your experiment could reveal conductance below 2E squared over H because of finite temperature effects, possibly other reasons associated with non-idealities of your device. So, I've taken a kind of theorist limit here where I focus on clean superconductors, nice gap, zero temperature, zero bias voltage, but that theorist dream doesn't often align with experimental reality. And so there can be departures for a variety of reasons.
Yeah, we all experience that, I guess. Yeah, all right. I guess because of time constraints, I will move to the next speaker. And if you could answer the rest of the questions in the chat, that would be great.
I'd be happy to. Okay, thank you so much for your attention,
thank you,
everybody.
and thanks to the attendees for their great questions. So our next speaker is Dr. Rolando Somma. If you could share your screen. So he's a technical staff member at Los Alamos National Lab, and he's also an adjunct assistant professor at the University of New Mexico. And today he will give a talk on quantum simulation with quantum computers. Rolando, are you there? We cannot hear you.
Hello, can you hear me?
Yes, now we can hear you.
Okay, so can you see my screen?
Not yet.
Not. Okay, just 1 second, please.
Mm-hmm.
Let's see if this works. So, okay, share screen. When I select share screen, it is asking me if it is only the host or all panelists. Do you know what that is? It's not giving me an option. Yeah.
Are you attending with a different account as well?
No, no, I mean, I.
Okay, so maybe David can help you.
Yeah, it's not giving me the option to share my
screen.
My screen, yes.
You're a co-host, so it should be.
Yeah, I saw that you were a co-host, so.
Withdraw and then try to give you those permissions again and see if it works.
Okay, I guess you should be able to share it right now.
Sorry, 1 second, please.
Sure.
So it's asking me to quit Zoom. Will not be able to record the contents of your screen until it is quit. Maybe I should log out and come back again.
Sure.
Sorry for taking time on this, but
that's all right. Okay, I see him. I think he's back. All right, there we go. We cannot hear you though. All right, there we go. I think we are back. Hello?
Hello? Can you hear me now?
Yes, yes.
Okay. All
And
right.
we can see your screen as well.
Okay, sorry for the complication. And
all right.
okay, so
take it away, please. Thank you.
Yes. Okay. All right. So I'm Rolando Soma. I work at Los Alamos National Lab, and part of the work that I do is on quantum computing, and in particular, I'm interested in developing quantum algorithms for fault-tolerant quantum computers, such that once we have one, we'll be able to solve interesting problems with it that we could not solve otherwise. So this talk will be about quantum algorithms for simulating quantum systems, which I personally believe is one of the main applications for quantum computers once we have one. And I hope to give you a tour on quantum algorithm design with a specific purpose for simulating quantum systems. So what is the goal here? What we're trying to do is basically simulate Schrödinger's equation that determines the evolution of a quantum system. For example, we have this spin quantum system here on the right, and we have a Schrödinger equation. And our goal is to simulate, to compute this equation by using a quantum technology, quantum computing technology. So here, h of s is what we call the Hamiltonian of the system that may depend on time. S is the time parameter here. And the goal is perhaps to compute some property of the quantum system, such as a magnetization correlation function, after it has evolved for some time t. All right. So you might think, well, this doesn't seem to be a hard problem, and there seems to be many options to do to resolve this problem, and we'll investigate various options for this. So, you might think, okay, well, why is that? Looks like a simple differential equation. In principle, I could try to solve this with my computer. But it turns out that if you do that, we know that this is actually a surprisingly hard and even an intractable approach. Even for a small quantum system of little n spins, the space dimension grows exponentially with this little n. And if we want to even writing down the matrix for the Hamiltonian already would take exponential time. Representing the vector, the quantum state, also would take exponential time. So to give you an idea, even storing a vector for, say, 70 spins, 70 qubits, with only y byte per entry for that precision, already requires order of all the information transmitted in the internet in 1 year. So we are very, very limited in using this approach due to this exponential increase in memory and complexity, if we were to try to solve Schrödinger's equation exactly. So this is like a no-go. And then, you might say, well, why aren't we more clever and try to come up with a better approach that does not indeed require this exponential growth of memory? And indeed, this has been explored. Certain well-known approaches for this are, for example, quantum Monte Carlo or density matrix renormalization groups. And indeed, these methods may not require exponential memory. And sometimes they work, they are efficient, but they work for very small classes of systems. They don't work in general. For example, the MRG stops working when entanglement grows large. These are serious limitations that we are aware of. Quantum Monte Carlo might not work when there is a sign problem, for example. So this is another evidence that simulated quantum systems in general with classical computers appears to be hard, even if you come up with better and more efficient and more clever ideas. You may think, okay, well, why don't we just do the experiment? Indeed, this is something that is done. This is, comes under the umbrella of quantum simulators, and there's various technologies like optical lattices, ion traps, other technologies like mutual atoms or NMR, and this approach indeed works, and indeed they provide the first demonstrations of quantum simulation. But the key limitation here is that we can only simulate one quantum system at a time. We have very little control. And these approaches may be prone to errors, uncontrolled errors, such that once we want to simulate like large quantum systems, the errors the coherence that can come in various forms, for example, decoherence, can kick in and lose the quantum information. So the fourth attempt, which is the one that I will describe here, is to really build a programmable quantum system now, quantum technology, that can mimic many classes of other quantum systems where errors can be kept under control. So once you are at this level, you are really thinking about a quantum computer. This was the idea that Feynman proposed back in the 80s. He knew that simulating quantum systems with classical computers seemed to be a challenge, probably an intractable problem. We do believe that that's the case. And he thought that if we were closer to nature, if we really developed a computer that was governed by the laws of quantum physics, then we would have some hope that such a computer could simulate quantum systems efficiently. So my talk will be about this, about quantum algorithms using quantum computers for simulating quantum systems. All right. And this is the main question that I will address in the rest of the lecture. But if you want to know the answer now, the answer is yes, and it's a positive answer that if one day we have a large and fault-tolerant quantum computer, we hope we have a lot of evidence that such a computer will be able to solve, to simulate quantum systems efficiently. All right. So quantum simulation is actually an extremely active field of research nowadays in quantum computing. It's a very interesting problem in my view because it combines the foundations of physics and information theory. It connects physics with computer science. Quantum simulation is known to be the problem for a quantum computer. What I mean by this is that any quantum algorithm that we have can be cast as a quantum simulation problem. It can be related to a quantum system and simulating such a quantum system. Now, besides applications in physics, like for example, computing scattering amplitudes, correlation functions, we know that quantum simulation naturally appears as a subroutine in many other powerful quantum algorithms, like, for example, quantum algorithms for solving linear systems of equations or optimization and other quantum algorithms as well. So while a lot of progress has been made for quantum simulation algorithms, there still remains many important open questions. In fact, I believe that improved Hamiltonian simulation methods will still be needed for a first demonstration. So in the rest of my lecture, I will summarize some of the most useful techniques and results that we have in this field. There won't be enough time to go over every existing result because every day there's few papers about this topic. In particular, I will focus on simple examples just to reduce the technical complexity of the lecture. But the results that I present can be generalized to more complex quantum systems and can address even other models of quantum computation. Indeed, quantum simulation is the main example of an exponential quantum speedup. It's not the only one. You probably heard about algorithms like Shor's algorithms for factoring integers, where there is an exponential speedup as well. Those algorithms in principle appear to have nothing to do with quantum mechanics, so it's kind of like surprising. And if you are interested in the variety of quantum algorithms that we develop, I suggest you go to this website, the Quantum Algorithm Zoo, where there's about more than 60 quantum algorithms that are displayed and explained together with the speedups. So this talk will be with a focus on quantum simulation, simulating quantum systems, and as I said, quantum simulation appears as a subroutine of many of these other algorithms in this website. So when talking about algorithms and developing algorithms, we need to have a little understanding of complexity. So in complexity theory, we typically separate approaches in efficient versus inefficient. there's going to be a problem size, which I call little n here. And that little n, for example, may be related with the number of qubits of the system that I want to simulate. Okay, so we are really after efficient approaches. Efficient approach is one where the running time of the algorithm, the overall complexity, scales only polynomially with that problem size, like, for example, linearly with n or quadratically with n. Inefficient approaches are those for which the running time may scale exponentially with the problem size. Those are the approaches that we don't want to obtain. So here, for quantum simulation in particular, we're interested in approaches where the running time is polynomial. Now, you might ask, okay, what happens with an approach that whose running time is, say, n to the 11th power, right? 11th power seems to be extremely large. Well, under these definitions, that approach would be efficient, but probably wouldn't be that practical. So when we have algorithms where the running times are like these large powers, even though they are polynomial, I mean, more investigation will be needed to really bring down such a degree of polynomial as down as possible in order to make these approaches practical as well. So we typically separate problems in their complexity classes. There's a well-known complexity class, which is called NP. NP are those problems for which the solution can be verified efficiently in polynomial time on a classical computer, but it may take exponential time to find it. So those are hard problems. The NP complete problems, the NP hard problems that you probably heard, those are really hard problems for classical computers. We have the class P, which is a class of problems that can be solved efficiently in polynomial time on a classical computer. And we also define a new class which we call BQP for those problems that can be solved efficiently on a quantum computer. So quantum simulation in particular is a problem that belongs to the class BQP. It can be solved efficiently on a quantum computer, but we strongly believe that there is a problem that cannot be solved efficiently on a classical computer, and that's the reason why we claim that there is an exponential quantum speedup. If you probably heard about the use of quantum computers for optimization problems. Well, it turns out that hard optimization problems are those problems that are hard for the class NP, they are complete. And those problems, indeed, we also expect that are even hard for a quantum computer to solve as well. So quantum simulation appears as the problem for a quantum computer. Everything reduces to it, and such problem can be simulated efficiently on quantum computer, while we don't believe that that is the case for a classical computer. All right, so the algorithms that I will describe here are developed in what we call the gate-based model. So I'll give you a quick tour on what the gate-based model of quantum computing is. So in this case, we assume that the quantum computer is made out of a certain number of qubits, like little m qubits. And anytime the state of the quantum computer is a pure state that can be described as a linear combination of all possible states of those m qubits, zeros and ones. So all the possible combinations, and this is a massive linear superposition where the dimension is exponential on that little m. So this is the way that we can describe the state. We'll never do this because this could be subject to exponential complexity, but it's just a property of quantum mechanics that the state can be described as a superposition of what we call basis states. Operations on a quantum computer, on a qubit quantum computer, are unitary operations. These are one of the postulates of quantum mechanics. So in this model, in this particular model, the gate-based model, we will think of operations as what we call like 1 and 2 qubit operations. So 1 qubit operations are transformations that state on a 1 qubit state. 2 qubit operations are also unitary transformations that act on 2 qubit states. These are some examples. You know, they sometimes come with these H's and X's for Hadamard gates or Pauli gates, control node gates, and things like that. But these operations are unitary and they act at 1 qubit or 2 qubits at a time. There is an important theorem in quantum computing that says that any unitary operation that acts on this large Hilbert space of m qubits can be decomposed as a sequence of 1 and 2 qubit gates, or at least very well approximated by such. So this is the way that we operate on a quantum computer made out of qubits. We start with some initial state, we implement these 1 and 2 qubit operations, and then at the end, we make a measurement, because the measurement is what is going to give us some classical information, like, for example, a bit string that encodes the information about the problem that we want to solve. This is a simple measurement. We call it a projective measurement to be consistent with the postulate of the quantum mechanics. And the outcome is typically probabilistically, and where the probabilities are given according to Born's rule, which are, they go with the square with the amplitudes, basically, with the absolute value of the amplitudes. So yes, the outcome of the measurements are probabilistic, and perhaps if you want to compute some expectation value, you have to run the algorithm, the quantum algorithm, many times in order to achieve the desired precision at the end. All right, so what is the challenge?
Before we move
Yes.
further, there are two questions about the
Sure.
complexity diagram that you showed earlier on slide
Yes.
20. So the first question is, what are the stronghold distinctions to p-space problems and BQP problems?
Sorry, I couldn't hear. Can you repeat the question?
Sure. What are the stronghold distinctions to p-space problems and BQP? And that was in slide number 20, I believe.
So is a question about the distinction between p-space and BQP?
Yes.
Okay, so we believe p-space is significantly bigger. And it's also, yeah, I mean, there's many questions that we, many things we don't know in complexity theory. So BQP is just the class of problems that can be solved efficiently on a quantum computer. We don't even know, you know, how to. Okay, so I would say many of these questions remain open.
Okay, the second question is, in BQP, are there problems that are neither P or NP? Again, in the diagram that you showed in slide number 10.
Yes, so yes, and probably Hamiltonian simulation is one of them. The reason for this is because in quantum mechanics we really have I mean, the outcomes are probabilistic, so we assign, I mean, the way that we define the BQP class is you know, basically with the probability on the outcome. So Hamiltonian simulation is like a BQP complete problem, and we believe that this is an example of a problem that may not be in NP.
Okay, so another question is, what are the other types of quantum computing other than gate-based ones?
What are the other types of quantum computing besides?
Yes. Besides gate-based models?
Yes, so that is an excellent question. So in this gate-based model, we implement 1 and 2 qubit gates. But I mean, this really, there's another model which is like called like a Hamiltonian-based model or a controlled Hamiltonian model, in which we can implement other types of interactions. For example, touching multiple qubits at a time, doing, you know, continuous evolution more than this discrete approach that I'm considering here. So yes, there are other models. You know, I mean, we don't have to be constrained to this qubit model. We may one day think about perhaps implementing a fermionic model of quantum computing where, you know, we work with the different particle statistics. So the gate-based model is the one that is mostly explored and is the model for which we have quantum error correction, while for these other models, we don't really understand whether quantum error correction is possible or not. So this is one of the reasons why we focus on the gate-based model, but it's certainly not the only one.
Okay, great. Thank you. That was the
Okay.
all of the questions we have so far.
All right. So I'll keep moving. All right. So So the challenge here is really to use this gate-based quantum computer made out of qubits to simulate this evolution under Hamiltonian HFS to simulate Schrödinger's equation. So the way that we are going to do this, and certainly it is not the only way, because at the end we only want a number, like a magnetization, a correlation function, right? But the way that we are going to do this in the approaches I will discuss later is by really preparing the evolved quantum state on such computer, or a state that encodes the evolved state in some way. So at the end, what we are really after is a sequence of 1 and 2 qubit gates that represent the quantum circuit that prepares such evolved state. What is the state psi? at time t, okay? And we want to do this with some sort of convergence guarantee. We want to come up with a method that says, yes, if you follow this recipe, you're going to prepare that state within some precision. So typically quantum algorithms are described then as just, we start with some simple initial state, psi. Okay, maybe this is something that can be easily prepared on a quantum computer, like for example, all qubits in the 0 state or 1 state. Then there's going to be a unitary evolution. That unitary evolution, as I said, has to be described with 1 and 2 qubit gates. And then at the end, we're going to measure an observable that gives us the information that we are trying to, that has information about the solution of the problem. So really at this point, it's like encoding the problem similarly, for example, spin system on a quantum algorithm, coming up with a quantum algorithm, and then decoding the information after the measurement that is going to give me the information that I'm seeking for the quantum system. So when constructing quantum algorithms in general, and not only for quantum simulation, we need to focus on resources. So these resources might come as number of qubits that we need, the number of fresh ancillary qubits, the number of measurements, number of repetitions of the algorithm, number of 1 and 2 qubit elementary gates, and any additional complexity coming for example, a pre-processing or post-processing step where we have to decode the information of the measurement to understand what the, for example, a correlation function is and so on. We mostly focus on the number of 1 and 2 qubit elementary gates when we look at the resources of quantum algorithms. It's not the only important resource, but it's one that tells you, gives you certainly very important information about the overall complexity of the quantum algorithm. So certainly understanding the number of 1 and 2 qubit elementary gates to implement the quantum circuit is a quantity that's very important in the design of quantum algorithms. All right, so as I said at the beginning, I'm going to take a simple example, and the rest of the talk is going to dive into a few quantum simulation methods. So the simple example is really taking a qubit example, because then there is no much effort that I need to do to encode this quantum system on a quantum computer that is made out of qubits. I'm going to consider the Hamiltonian interactions are time independent, okay, just for simplicity. H here is time independent. And with no loss of generality, I can write it as a linear combination of interactions, for example, nearest neighbor interactions or things like that. So here the coefficients CK are with no loss of generality, real numbers, might be bounded. I'm not considering units here, but certainly if you are at the end, you know, we could consider units and make everything plausible with the complexity of obtain. For simplicity, I'm going to consider these operators OK here are products of what we call polyoperators. Polyoperators define the algebras for qubit systems. For example, you know, one such polyoperator could be the tensor product of a poly X acting on qubit J and a poly X acting on qubit J plus 1. This could be like a nearest neighbor type of interaction. These operators X are a particular operator, a poly operator that, for example, flips the state of the qubit, maps 0 to 1 and 1 to 0, certainly not the only one. There's X operators, Y and Z's. Their matrix forms are here. When talking about many qubits, we need to consider the tensor products of such operators. So for simplicity, I'm just thinking of an n-qubit system where the interactions are described by these products of polyoperators, and this is a standard practice when describing the Hamiltonians of qubit systems using this type of operators. It's not the only one, but it's standard. So the Hamiltonian simulation problem, in more detail, is a problem about approximating the time evolution, the solution of Schrödinger's equation, as I said at the beginning. So we are given the Hamiltonian H, say as a linear combination of poly products, as I described before. Then there is an evolution time t, okay, greater than 0, and a precision parameter epsilon, which is greater than 0. So our goal here is to construct a quantum circuit giving us a sequence of 1 and 2 qubit gates, such that if we act with such quantum circuit to the initial state psi, is approximately equal up to an epsilon error to having acted with the evolution operator. This is a solution to Schrödinger's equation acting on the initial state psi. And we want this in principle for all initial states psi. We don't want to make a difference between certain states and leaving behind others. Although, I mean, in some contexts, a restricted initial state may also be of interest. All right. More generally, we might consider that our quantum computer will have some what we call ancillary qubits, some additional qubits, so that they may act as a catalyst. So now this unitary V, the quantum circuit, perhaps acts on more qubits than the qubits that describe the original quantum system. But at the end, it kind of like reproduces the evolution on the part of the quantum state that we want, up to an approximation error epsilon. So many of the quantum algorithms for quantum simulation do this. They require not only the qubits that represent the quantum system, but also some additional qubits that, for example, they start in some simple initial state like the all zero state. All right. So at this point, it's really kind of like a linear algebra problem in some way. We have this massive exponential operator. Okay, the Hamiltonian is exponentially large in dimension. We never want to compute this guy because that would take us exponential time. But we want to come up with a smart way of implementing this exponential operator, a solution to Schrödinger's equation, as a sequence of 1 and 2 qubit gates, represented this by a quantum circle. So it's kind of like a factorization problem. All right. So we want to achieve this goal not only by providing an efficient approach, something that scales polynomial with the system size, okay, in overall running time, but in principle, we want to find the best possible method in terms of overall resources, right? So that's our main goal here. So to this end, I mean, since we don't have a large quantum computer, we certainly need to develop certain analytical tools that can demonstrate that whatever we've done to simulate the evolution operator, it converges. We cannot try and see what happens because there's no such large quantum computer, or just run a small numerical simulation, say on my laptop, because that would only give us partial information about small systems and particular quantum systems, right? So here we are really aiming at having nice convergence guarantees of whatever approach we follow, and that it scales very nicely, say, with the system size. All right, so I said the best possible approach, right? And what is the best possible approach? Well, it's not that we can really bring the complexities as down as as we want, and there's and the reason for this, or at least we have evidence that that is not the case, is that there's a number of results that come in the name of no fast forwarding theorems. These results basically place a lower bound, at least in various models of quantum computing, like the Oracle model. They place a lower bound on what the gate complexity, the quantum complexity of the quantum algorithm is going to be for simulating certain classes of quantum systems. For example, for qubit systems, say in a 1D lattice or a 2D lattice, we have some evidence that at least we need complexity that is linear in the volume of the system and linear in the evolution time. Okay, so we will never expect to have sublinear in N or sublinear in T complexity for large classes of models, of qubit models. Okay, so a little bit of history on this before I dive into the various approaches. So we knew actually for a while that quantum computers in principle could simulate quantum systems efficiently in polynomial time. There's a seminal paper by Seth Lloyd in 1996 that discusses the approach based on product formulas, these universal quantum simulators. That is considered kind of like the first paper that's been shown that quantum computers in principle could simulate quantum systems efficiently. But it hasn't been until more recently, in 2015, that we came up with fairly efficient approaches for this problem. Okay, and this comes in the name of Taylor series method. I will briefly discuss how these methods work. We brought down the complexities of product formulas, at least in more general case, substantially, making quantum simulation closer to reality. As I said at the beginning, we expect that all these improvements will be needed for a first demonstration of a quantum simulation. More recently, in 2017, there was another idea that came under the name of quantum signal processing. It's also based on function approximation, like the Taylor series method, and it reduces the overall complexity in terms of gates. It's not too different, but it reduces the number of ancillary qubits that we need, and it's a very nice approach. and also achieves very nice scalings in terms of all the parameters I enter into the problem. So for this talk, I will briefly describe product formulas. I will briefly discuss our Taylor series method, and time permitting, I'll discuss a little bit about quantum signal processing, although I probably run out of time based on the delay that I had at the beginning. All right. Okay, so how is that product formulas work? So product formulas, I mean, they are kind of like attractive because they are simple. I explain how they are. They are fairly intuitive. They are already using classical algorithms, like, for example, Monte Carlo. They don't need ancillary qubits. So they are kind of like attractive for near-term applications of quantum simulation. So the idea behind this approach is that we're going to approximate the evolution operator, this e to the minus iht, but short-time evolutions under the constituents of the Hamiltonian, all these OKs that we have. And each of those is easy to simulate using, say, 1 and 2 qubit gates. So that already is going to give us a quantum algorithm for simulating this. A property of this product formula is that it exploits some structure of the problem, like commutation relations, and I discuss this a little bit later. But the downside is that their complexity is not the best. In terms of accuracy in particular, it's kind of like poor, and this could be a prohibitive scenario for some applications. All right, so we start again from our n-qubit system, all right? And now what we're going to do is approximate the evolution operator as a sequence of evolutions under each of these interaction terms that appear in the Hamiltonian. So these are the evolution terms, Sj, and these are going to be very short times, and we'll have to basically control that in order to control the error. So each of these short-time evolutions is going to correspond to either an elementary gate or can be easily decomposed as a sequence of elementary gates. And the complexity of this approach is mainly determined by what is the number of these short-time evolutions that appear in the product. All right. This is what's going to give us the scaling. So, for example, here is a case where if we have a term that it wants 3 qubits, it is easy to decompose into 2 qubit gates. Okay. These are standard techniques in quantum computing that are used everywhere in the engineering of quantum algorithms. So a pith order product formula is basically a unitary operation that approximates the evolution operator U, okay, such that the error comes at order p plus 1. So p here is an integer, is a positive integer, and the fact that this error is quadratic or bigger is what can allow us to control the errors by using this approach. So what we're going to do is basically we have to split the overall evolution time t into r segments of sufficiently small time s. And now what we're going to do is to approximate the evolution operator by using a product formula that approximates the short time evolution for time s r times. So, for example, it is well known that the first order product formula, where the error appears at second order in S, is just the product of evolving with each of the terms of the Hamiltonian. If your Hamiltonian contains only 2 terms, it's evolving with one and then with the other. And second order approximation is given by this type of product formulas. We evolve with one of the terms for half of the time, then the other, and then again with the first one for half of the time. In fact, there is a recursion relation that allows us to push the order of the approximation as large as possible. This comes with an overhead due to the number of terms that appear in the recursion relation, and these things are certainly investigated when determining the overall complexity of this approach. So these product formulas are fairly easy to analyze. We can actually compute or have analytical forms for the error. And typically having such analytical forms are useful in order to understand the convergence guarantees. Those errors depend on the commutators of the term that appear in the Hamiltonian or nested commutators of those. So like if the terms are commuting, then there is no error. Or if the terms are mostly commuting, you know, or the commutators are small norm, then the errors are smaller. And certainly people have investigated the things and trying to explain the structure of the Hamiltonians in order to provide better and better error bounds by using this type of approaches. So overall, I mean, and without going into details, again, we are going to approximate the evolution operator by using these product formulas for short times, hard times, and one can bound the errors by just having very simple expressions, very simple bounds for it. And the overall result is that the gate complexity has certain dependence. This is the order notation, denotes the asymptotic scaling is hiding perhaps some constants. If that is, in this particular case of the Cuban system, is linear in the number of terms that show up in the Hamiltonian. Is superlinear in lambda. Lambda is like the norm of the Hamiltonian, is the sum of the coefficients, the interactions. Is superlinear in the evolution time and depends on the precision parameter as 1/epsilon to some power, where this p again can be 1, 2, is some positive integer. So as you may see from this expression, is that these product formulas provide an efficient quantum algorithm for simulating quantum dynamics because there's no exponential complexity, there's no polynomial complexity in the dimension, in this big N. Everything is linear, for example, in K or lambda, and all the things are going to be polynomial in the volume of the system with each is little n. So this is already an efficient approach. All right, so people have investigated the usefulness of this product formula for example, simulating quantum chemistry, the dynamics of quantum reactions and things like that. You know, we have polynomial complexity, but you might ask, okay, how well does it perform in practice? This has been investigated for the last few years. You know, if one applies just a blind approach and simple error analysis, then one can show that the complexity is pretty bad. Actually, it goes with the number of terms that appear in the Hamiltonian for this particular problem to the 11th power. But with time, people started to think about better approaches that require compilation of algorithms, doing things smarter ways, separating terms in the Hamiltonian in different ways, and bringing down all the complexities to lower and lower powers. There's a number of papers for this type of problem because we think that quantum chemistry might be one of the main applications for quantum computers once we have one. All right, so there's been considerations of how to improve product formulas or their scaling by using randomization approaches. There's a number of papers here, also by constraining, for example, the initial state to be low energy state or to have some symmetries. As you might think, the more structure I put into the problem, then the better error bounds I can obtain, and this is indeed the case. And there's a number of very recent papers discussing all these ideas. This is just one example of a recent paper of mine and my postdoc Burak Sahinoglu on where we show that the worst case error for product formulas, which are the ones that we typically analyze, do not really apply when, for example, the initial state is supported in some low energy subspace, and better error bounds can be obtained. So this is kind of like an area that it deserves further exploration because we really want to bring these error bounds as down as possible to improve the complexity of the product formulas. All right, so you might ask, okay, well, is this the end of the story, or are there indeed better quantum simulation methods? And I showed you at the beginning that we knew about product formulas from 1986, at least in the context of quantum computing. And it wasn't until more recently, in 2015, that we came up with a new quantum algorithm that does something different. It aims at simulating Taylor series expansion of the evolution operator. I explained this. And we can show that this new approach is actually optimal in the sense that we are almost satisfying this no fast forwarding, this lower bound of the no fast forwarding theorem. But it has a very nice scaling in terms of the precision. It's polylogarithmic. And this is kind of like an exponential improvement in the dependence on the precision parameter with respect to product formulas. And there's been some excitement on quantum simulation algorithms system on how to improve these methods even further. So in the next few slides, I explain this. I'll have to go quickly. I don't want you to get caught into the technical details, but at least I have to mention them at the high level how they work. And certainly I'd be happy to answer more questions by the end about how the technical components of these algorithms, if you really want to understand more. All right, so This Taylor series approach, the truncated Taylor series approach, I mean, one of the downsides is that it needs these ancillary qubits. Okay, so we need more qubits than the n qubits that describe the quantum system. And they don't exploit the structure of the problem, although there's some current work that is going into this. And I'll talk a little bit more about that later. So we are not going to simulate the evolution operator by evolving with each of the terms of the Hamiltonian here. But what we are going to do first is to express the exponential of the evolution operator as or approximated as a truncated Taylor series. So our goal at this point is really to implement a unitary operator that approximates this Taylor series expansion. So one thing to note here is that this, even if we truncate the Taylor series, but if the order of truncation is large, this operator I call W of S is not going to be exactly unitary, but it's going to be almost unitary because U of S was almost unitary and the precision or the error in these approximations is going to be very small. The quantum simulation algorithm will try to implement the truncated Taylor series for short times S, okay? And we'll do this a number of times Q, where S is basically the overall evolution time divided by the number of steps or number of segments Q. And we want to satisfy an approximation error, again, that is given by some given epsilon. This approach will use two quantum primitives that we develop specifically for the problem, one which is called LCU, stands for linear combination of unitaries, and the other one that is called OAA, which stands for Oblivious amplitude amplification. So if you know how Grover's algorithm works, it uses amplitude amplification. This is kind of like an extension of that technique to a case in which we don't really know what this initial state is. So one of the key points here is that the overall complexity is only going to be polylogarithmic in 1 over epsilon rather than polynomial in 1 over epsilon as the product formulas were. This is where there is an exponential improvement in terms of epsilon, complexity dependence on epsilon. And the main reason, the key reason for that is because when we approximate the evolution operator as a Taylor series, we can cut off, or we can put that truncation R basically at an order that is polylogarithmic in 1 over epsilon. So this is the main reason why we achieve that scale. All right, so I said one of the primitives that uses is LCU. It stands for linear combination of unitaries. I'll give you a short tour on how this works, right? So at the beginning, I said that quantum computers are good for implementing unitary operations, but what about linear combination of unitaries? Well, it turns out that something can be done whenever we have a linear combination of unitaries. So say that we have a quantum state psi, and now we want to map it to a linear combination of unitaries, alpha B1 plus beta B2, where B and 1, B2 are unitary operations, alpha and beta are coefficients, you know, with no loss of generality. I may assume these are positive and add up to 1. And I want to do this type of transformation that might not be really like acting with a unitary on psi. So there is a nice quantum algorithm primitive that can do this, and it's the following. We start with state psi, and now we add one ancillary qubit that encodes the information about the amplitudes alpha and beta by acting with a unitary operation B on that state 0. Next, we implement a unitary V1 control, say, in the state 1 of the ancilla, a unitary V2 control on the state 0 of the ancilla, 0 and 1. And then when do the operation V dagger, and if you do the math and look at the quantum state that is output by this quantum circuit, there's going to be 2 branches, one that is flat by the 0 state of the ancilla, another that is flat by the 1 state of the ancilla, and the right linear combination of unitaries are flat with the 0 state of the ancilla. So this is, again, is a linear combination of unitaries, not necessarily a unitary operation, and this is the reason why we have these 2 branches on the quantum state when we look at the end. Now, what happens here is the following. According to the postulates of quantum mechanics, if we were to measure the ancilla and obtain the 0 state, then we implemented the right operation on the state, the right linear combination. But if we measure 1, then we would be implementing the wrong linear combination of unitaries on that state, and that would be an error. That's going to be a probability of having the right solution, which is given according to Bohr's rule. All right. So here we are not going to do a measurement, because if we do the measurement and we have to do this many times, the probability of success would going to decrease exponentially fast in the number of measurements. For this and for improving that probability of success and boosting it up to 1, we developed what we call the Oblivious amplitude amplification technique. So the way that it works is the following. I'm going to write W as this whole unitary operation, this whole quantum circuit that does not prepare the right state, but it prepares a quantum state where one of the components is the right thing. And I'm going to further assume that, for example, the linear combination of alpha v1 plus beta v2 matches exactly half a unitary. It turns out that in that case, the following quantum algorithm actually prepares with probability 1 the exact state that I wanted, which was alpha v1 plus beta v2, this linear combination of unitaries acting on that state. So the reason for this can be seen geometrically. The quantum algorithm I just described can be seen as two reflections in this two-dimensional Hilbert space. Again, I don't expect you to remember all this, but I just want to point out that this is related to the amplitude amplification technique used in Grover's algorithm, where two reflections basically is a rotation. So what I'm doing is taking the state that has some probability of success of being in the right thing, and doing a rotation and mapping it with probability 1 to the right state that I want. All right. Certainly, I described just for a linear combination of two unitaries, but it can be extended, that approach, to the linear combination of many other unitaries. So what we're going to do here is that first, we approximate the evolution operator by this truncated Taylor series. The Hamiltonian is a linear combination of unitaries, these polyproducts. So at the end, this operator W of S is a massive linear combination of unitary operators. So now this fits well the framework of linear combination of unitaries, okay? And then, the rest is just really picking up the parameters such that, for example, this linear combination is almost half a unitary, so we can use the LCU approach together with Oblivious amplitude amplification. All right. So once you put everything together, okay, it turns out that the gate complexity of this approach can be shown to be almost linear in the evolution time up to logarithmic correction, okay, which is better than what we have for product formulas. Almost linear in the norm of the Hamiltonian lambda, again, up to logarithmic correction, but it is only a logarithmic dependence on the inverse of the precision parameter. And this is what made this improvement really exciting, because we now, the number of resources in terms of precision is really, or scaling, is very nice. And in fact, we can show that for worst case instances, this gate complexity is optimal. Okay, so there is a much lower bound coming from a non-fast forward NTR. All right. Okay, so certainly after we came up with that paper, people investigated its application to quantum chemistry. They were able to bring down the power, the scaling of product formulas further down by using this approach. And again, in terms of precision, the scalings are really nice now. And a couple of years after that paper, Lo and Chuang came with this new idea of quantum signal processing, again for simulating quantum systems, which is again based on some functional approximation. The Taylor series approach basically tries to implement an approximation to the Taylor series of the unitary operator. This new approach is trying to implement an approximation of another decomposition of the unitary operator. So one of the key things of this quantum signal processing approach is that it doesn't need these ancillas, okay? The Taylor series approach needs these ancillas to encode basically the amplitudes that appear in the linear combination of unitaries. Here, that is not the case. It uses a different approximation of the evolution operator, of the exponential operator, for example, by using Bessel functions of the first kind. Again, these things are a little bit technical, but this is a really nice idea. And
we have 10 minutes left.
Okay, all right. Yes, I'm getting there. So and the way that implements such linear combination is by using these nice gadgets in which we have the qubits basically represent the system with one additional qubit. It's a little bit more technical than this. There's some details I'm leaving behind. But the idea here is that, again, once we are at this level in which we want to approximate the evolution operator by some polynomial and some unitary W of R, then it turns out that there is a simple gadget that what it does is it adds one ancilla, and now there are these phases, and such that when you look at the overall operation that is implemented by the end, it's really an operation that can be described as a polynomial of these W's, these unitaries W. So the challenge here for this approach is really finding these spaces. This sorry, my cursor got stuck, I think. Probably I need to end the show. Sorry, I have to. Okay. So the real challenge here is to finding these algorithm, these angles that are these 1 qubit rotations, such that at the end I implemented the right polynomial in W, okay, that I wanted to do, and knowing that that polynomial is going to be a good approximation of the evolution operator. Again, this approach has a scale in terms of precision that is polylogarithmic in 1/epsilon, and the reason for that is because there are fairly good approximation, function approximations terms as polynomials of W of the evolution operator. All right. So so I just going to mention briefly additional considerations that I didn't discuss in this talk, mainly due to time constraints. So I assume, I consider this simple example of a Hamiltonian that was a qubit Hamiltonian and was time independent. You might think, okay, what happens when there is a Hamiltonian that is changing in time? Well, it turns out that the methods based on product formulas and Taylor series that I explained can be easily generalized to that case, to the time-dependent case. Product formulas, their complexity is kind of like large in terms of the rate of change of the Hamiltonian. The faster it changes, the more complexity we're going to have. The scaling for the Taylor series approach, when there is time dependency, is actually fairly mild. And this is another improvement, another advantage of that method over product formulas. So to achieve this nice scaling, what we basically did is, instead of approximating the Taylor series for the exponential operator, we need to approximate the solution to Schrödinger's equation in time-dependent case, which is a time order series. All right, and that can be found in our paper. Again, I consider quantum computer method of qubits, systems of qubits, so there is no much effort to encode this system and map it to quantum, right? I mean, to the algebra of quantum computer, but certainly people have investigated a method for simulating fermionic quantum systems or anionic systems or even bosonic systems. There's a number of works for that. One typical approach to this is to take the fermionic algebra or the anionic algebra and use some sort of mapping that operators are mapped to these poly operators, and then we can use all the machinery we have for qubit systems, right? So that is one approach, certainly not the only one. Simulating bosonic systems is more complicated because we probably need to set bounds on the number of bosons. We might be working with the Hilbert spaces that in principle could have infinite degrees of freedom, but we have to limit that in some way, since quantum computers made out of qubits, the Hilbert space is going to be finite. Again, I consider qubit systems. You might think, okay, what happens when simulating quantum field theories, simulating systems in continuous variables, and so on. There's a lot of work along these lines, a lot of recent work. Here's a few references. And again, the challenge here is that we need to discretize the system and work with finite degrees of freedom. And proving convergence is sometimes really challenging for this type of applications. All right, so I never discussed quantum error correction, okay? But the reason for that is that the algorithms that I describe are intended for the gate-based model. And we do have a full theory of quantum error correction that applies to that model, all right? So people are certainly interested in investigating whether quantum simulation could be the application for near-term, intermediate-term, noisy quantum technologies, NISQ devices. My take on that is that we still don't yet know. There's a lot of work going exactly into this problem. I think it's an important problem to investigate further and seeing whether we can do something along the lines of quantum simulation without using quantum error correction at all. At some scale or at some sizes that cannot be simulated with the classical computers. That is going to be a challenge, but perhaps there's a problem for which something can be done. All right, so just a few conclusions. Well, in my view, quantum simulation is expected, still expected to be the main application of quantum computers. Appears to be niche, but it's really an important problem in science all across the board. There's also, we're also in the case that we found so many advances in quantum simulation algorithms that I think that increased our confidence that this is indeed the case. Polynomial scaling alone might not be sufficient for practical reasons, but the fact that we have so many quantum algorithms for quantum simulation right now gives us some confidence that this is indeed the case. Quantum computers will be able one day to simulate quantum systems efficiently. In general, quantum resources are going to be very expensive. I described some quantum simulation methods, but we really need to keep thinking about how to bring down these complexities as much as possible. Where the right measure of complexity at the end is going to depend on the type of technology. Are bringing new qubits, ancillary qubits okay? Is that too expensive? What is better? Depth of quantum circuits, right? Or space? I mean, all the things are going to depend on the technology, on the type of errors, and so on. So right now we are at a stage where significant improvements in quantum algorithms for quantum simulation were made. But even for some important problems, like for example, simulation of quantum field theories, little is known about efficient approaches for this type of problems. So I think this is an exciting topic that has to be investigated further still. Another thing that I mentioned briefly is that quantum simulation algorithms, they are not only useful for simulating quantum systems. They find applications elsewhere, like, for example, simulating problems in linear algebra, optimization, and so on. We are starting to understand this better by mapping many of these problems to quantum simulation problems. So, and another perhaps take-home message here is that the recovery of power for quantum algorithms is really not easy. One might think about simple ideas that in my view, probably will not work well in general. I've seen this, for example, in optimization. People that think that quantum computers are really good for optimization, but we have little evidence that that is the case. And perhaps it's because those approaches are aiming solving like general optimization problems, and we really need to investigate these things further. So in my view, or at least in my experience, simple ideas typically don't work well in general, and maybe the resulting quantum algorithms are indeed highly inefficient. And certainly there's many open technical questions, like for example, can we improve the complexity of product formulas further in terms of precision, things like that? Can we reduce the complexity of these Hamiltonian simulation methods under other assumptions and initial states? You know, various methods are powerful in different cases. Can one design one single method that works well in general? And those type of questions remain open and are interesting in my view. So with this, I finish, and thank you very much. Be happy to take questions.
All right, thank you so much, Rolando, for that comprehensive talk about quantum simulations. That was really good. So I don't see any questions right now. I will just wait for a few minutes. I have a question though. So you showed the quantum circuit for that algorithm, and what was that gate B standing for in that circuit?
Sorry.
It was in slide number 58.
Okay, I can probably 58.
Yeah, this
Yes.
one. This B, gate B is.
Yeah, that's right. So I explained this kind of like generally. I said
Okay.
B1 here is a unitary and B2 is a unitary, but indeed each of those is a quantum circuit.
Mm-hmm.
Okay, so I didn't describe the internal structure of each of these Bs,
Mm-hmm.
right? So this is a framework that applies generally. I mean, not only for the quantum simulation problem, right? So it's a framework, you know, that implements linear combination of unitaries. When we come down to really applying this, for example, for simulating qubit systems, these V's are going to refer to 1 or 2 qubit gates, as I explained at the beginning.
I see.
That's going to be related to the terms that appear in the Hamiltonian, and those terms, I assume for simplicity, they were Pauli products. So yes, it's going to come down to that.
All right, thank you.
Thanks for the question.
I guess for the sake of the time, we have to move on to the next speaker, but thank you so much again.
Well, thank you very much, and I apologize for the
No problem.
delay.
All right.
Thank you.
So our next talk is going to be given by Stefan Wernli. So he's a senior software developer at Microsoft, and he will be talking about running on quantum hardware with Azure Quantum. All right. Thank you so much, Stefan. Take it away, please.
Hi, thanks everyone for joining. Let me see how to share my screen here.
So it's at the bottom, this green one.
There it is.
Mhm.
Okay, there we go. So I am going to be doing a demo walkthrough of executing on quantum hardware using Azure Quantum. Just a brief introduction to myself. As mentioned, I'm a senior software engineer on the Azure Quantum team. In particular, I work on the compiler and runtime team for Microsoft's Q# programming language, which you're going to be seeing some samples of today. The focus of my talk is really going to be on execution on Azure Quantum and kind of demonstrating what those tools and processes are like. But if you are interested in getting more information about the Q# language and going into more detail about that, I definitely encourage you to check out Maria Mikhailyova and Matthias Sokin's presentations on Q# and the Microsoft Quantum Development Kit Wednesday afternoon and Thursday morning. But for now, I'll go ahead and get started. So here I have a Visual Studio Code environment set up. In terms of some of the tools that I have, you can see I actually have the extension installed for the Microsoft Quantum Development Kit. And in addition to that, I have already created a Azure Quantum workspace on Microsoft Azure. Here I've got this set up with my personal account for some self-hosting. So this is a workspace that you can create in Azure today just by signing up and saying that you would like to participate in Azure Quantum, which is currently in public preview. As part of this workspace, I have a couple of providers configured. So I've got the Microsoft Quantum Inspired Optimization providers. I won't be getting into any details with those today, but I also have set up two quantum computing providers, one for Honeywell Quantum Solutions and one for IonQ, that are configured to allow me to submit jobs for execution on their endpoints. IonQ offers a simulator as well as a QPU, and then Honeywell offers an API validator and their, right now I'm configured with their H0 quantum system, this HQS LT 1.0. Now, if you are already familiar with Azure, things like workspaces and configuring things, interacting with your workspaces via the Azure Quantum, or via the Azure command line interface, are very similar to what you would do in Quantum is very similar to what you would do for existing Azure workspaces. But if you're not familiar with Azure, there can be a bit of a learning curve just recognizing and utilizing some of these tools. And so that's what I'll be showing off today. Just to give you an idea of what execution is like and to kick off our first job, if I navigate to our Grover sample that I'll be going into more detail on in just a moment, executing on a quantum system is as easy as specifying a command like this. I'm using the quantum feature of the AZCLI, submitting a job to the IonQ QPU target, giving it the convenient name of Grover so that we can recognize it later, specifying 5,000 shots, and then providing the input to the actual program. And I'm going to go ahead and kick that off so that it can run in the background while I review what this program actually is and how we expect it to work. So I've made my submission, and let's open up that program to take a look at it. So this is the Q# programming language. And our goal in writing this language and making it available is to provide developers a way to write quantum programs. This is more than just a circuit generator. It really is a full quantum programming language. And you can see that we have a lot of constructs available in it, like for loops and different kinds of classical calculations in order to prepare angles for rotations that you would expect to see in any kind of programming language, as well as quantum operations like this X and H that you see down here that are operating on a particular qubit. So I'm not going to go into much detail about this algorithm, but just as a brief overview, the Grover search algorithm is intended to identify a particular marked input that is flagged by a given oracle. And in this case, this sort of simplified Grover's algorithm is just looking for a alternating sequence of zeros and ones. So what I can do to experiment with this is I can actually run it locally against the full state simulator that's provided as part of the quantum development kit. And what that looks like is I can do a .NET build to just compile this, this program. And then when I want to run it against the simulator, I can say .NET run and give it a number of qubits, and let's say 4. Now, oops, dash dash. Now, when that runs, it's going to perform the quantum algorithm using our local simulator. So this is just running on my local machine. And you can see that it has identified the 4-bit alternating sequence that we'd expect, 0, 1, 0, 1. If I specify a smaller number of qubits here, then I, of course, get the smaller sequence out of it, in this case, just 0, 1. Now, this is all running, as I mentioned, on our full state simulator. So there's no noise modeling here. This is just modeling and simulating ideal qubits where every operation on those qubits performs exactly as you'd expect. But what I can do is take this exact same program that I wrote and was able to validate using local simulation and specify in the project file that I would like to have the execution target of IonQ QPU. Now, what this does is it gives a clue to our compiler that we're going to be executing this on a hardware target, and it takes certain additional compilation steps to ensure, as much as we can, that that particular program is compatible with that given target. But I can also pick other targets to execute against. It doesn't have to be the one that I specify. This is just the clue to the compiler about what sort of steps to perform there. So if I'd like to do an Azure Quantum submission, then what I want to do is use the AZ Quantum command line tool. So in this case, let's try doing a submission, but to the IonQ simulator. So if I say AZ Quantum job, submit, and I give it the target of IonQ simulator, now this is going to execute against the simulator that IonQ provides as part of their endpoint to Azure Quantum. And just for convenience sake, I'm going to give it the name Grover again to make this easily identifiable. Specify that I want the output in a table and give it a number of qubits as input. So you'll note that I'm not explicitly requesting a particular number of shots. By default, that just means that it's going to run 500 shots. So let's submit this to the IonQ simulator. And the output that I get will include the ID of the job that I just submitted. So now that we have that job ID, I can query the status, I can get the output information. Let's do an example of querying the status. Job show, give it that job ID. And let me make this a little bit larger so it's easier to see that table. And we can see, this has already succeeded and it ran against the IonQ simulator. We can also see the name that I specified here. So I should be able to get the results. So let's check out what the results of this job actually were. Output will show you the results. And again, I'd like to see it visualized as a table. And this will give me a nice histogram indicating the results. Now, this histogram is not actually that interesting. 100% of the 500 shots resulted in exactly the pattern that we'd expect, 0 and 1. That's not that surprising because in this case, the simulator that IonQ exposes is likewise a noiseless full state simulator. So it's not modeling any noise of their system here, but instead just executing the gates kind of on ideal qubits and getting us back exactly the result that we'd expect. This can look a little bit more interesting if I increase the number of qubits. So let's say 5. Submit that job to the simulator. And then again, take the ID and let's check to see if it has completed. Output. Okay, so this histogram is a little bit more interesting. On 5 qubits, or a 5-bit sequence, the Grover's algorithm, even when executed on an ideal simulator, a noiseless simulator, is not perfect. You have a very high likelihood of getting the marked input, but there's still a non-zero likelihood of, a non-zero but very small likelihood of getting the other results. And you can see that this simulator does report that. It shows that there is a low probability of getting some of these other possible outputs. Now, when we're executing against the actual hardware, in this case, I don't need to do any recompilation. I don't need to change anything about my algorithm. I would just need to submit against the IonQ QPU instead. Now, I have previously done one of these submissions, so let's go take a look at what those results look like. Switching back over to my Azure portal and taking a look at my workspace, you can see there is a job management view, which can show me the jobs that I've executed. And I can go grab a particular previous execution and copy that particular ID. So here's one that I've run against IonQ QPU previously. And on the workspace, you can download the results as a JSON file, or I can just take that ID and use the command line, which I personally am a fan of, to check what the job output was for that particular job. So here we can see an execution that actually occurred on quantum hardware, and it looks quite different than the one that ran against the full state simulator. In this case, we still got a very high occurrence of our expected marked input, 0, 1. But you can see some subset of the results actually show executions or particular shots that return values other than our marked input. And this is really great to see. This shows us that we are executing on actual hardware where there is real noise, where not every shot is going to execute perfectly, and gives us a good probabilistic output based on our execution. Looking back at our quantum workspace, we can see that the job I submitted earlier has actually succeeded. This was the 5,000 shot 5-qubit sample that I started with at the beginning of the session. And if I check the results of that one, let's see how well it turned out. Now, looking at that histogram, I get a quite, a little bit messier of a result. At this point, what I'm executing is a quantum program that's large enough that I'm kind of close to the noise threshold of the hardware. I wanted our execution to finish, so I didn't pick a huge number of shots. But as you increase the number of shots on hardware, you're actually going to see what you hope to see is that the marked input will become the highest result. Now, in this case, we didn't get that that particular result. Our marked input did not have a spike at it, but this is part of the challenge of executing on NISQ hardware, noisy intermediate scale quantum hardware. you have to figure out how to tailor your algorithms and tailor your parameters, such as the number of shots chosen, to the particular hardware and the noise characteristics of that hardware. And that's part of what Azure Quantum allows you to do, is to start experimenting with executing on quantum hardware today. So just to demonstrate the tool a little bit more, if I take the earlier histogram that I showed from the 2-bit Grover sample, you'll notice that I keep specifying -o table. If I don't provide that, the default output from the command will actually be JSON, which makes it nice and parsable. And this is the same JSON that you would see if we downloaded the results as a file from the quantum workspace. And this allows you to start building tools either around the AZ Quantum CLI or use existing Azure CLI functionality, like the AZ storage command that would allow you to download the files related to a particular quantum job. I won't go into detail about that, but you can imagine building a series of scripts that do multiple submissions across different inputs to a particular algorithm and monitor the jobs, download the results in order to identify particular patterns or do a full execution across that spread of inputs in order to build up a deep understanding of a particular algorithm and how that algorithm executes on quantum hardware. So any questions so far before I switch over to a different hardware example?
Yes, there are 2 questions so far. Mm-hmm. So the first one is, so you showed the results from the simulator, and the question is, where is the statistical error in the simulator coming from?
This graph here, where it showed it ran on the simulator, but it still had possibility for error of getting the incorrect result. In this case, rather than coming from noise, this statistical possibility for error is based on the actual algorithm itself. This particular implementation of Grover's search has different probability of success depending on the length of the bit string. So for a bit string 2, we actually expect an ideal quantum computer would return the correct result 100% of the time. But for a 5-bit string, even an ideal computer would only get it with 99.9% probability. And so that error is actually a result of the algorithm itself. As far as the internals of the simulator and how IonQ simulator calculates the particular frequency of these results, I don't have visibility into the implementation of IonQ simulator. What I can say for the QDK simulator that's built in to the language that allows you to do these simulations locally, you will see a similar error probability. You would just have to run the program multiple times. For local execution, each run of the program is effectively a single shot. And so you would want to either update your program code to run the algorithm multiple times and then output a full spread of results, or write a script around a single execution to kind of simulate the idea of executing multiple shots. If I were to do that against the local simulator with a high enough number of repetitions, I should get probabilities that match what we're seeing from the IonQ simulator here. It's just with a probability of getting an alternate result of just 0.0, I guess, 1 minus 0.999. It would take quite a few executions for us to see one of those invalid results come back.
Okay, I hope this answers the question. So the second question is, it sounds like you have to know the result in order to choose the correct hardware parameters. Is that correct?
Well, that is a very interesting question that I think is perhaps a little bit broader than the particular subject of this talk, but I'll do my best to give the short answer for it. There is an entire, I guess, area of research around this idea of how do we identify the correctness of a particular quantum execution. Obviously, if you already know the error characteristics of your hardware, then you have a good idea about whether or not a particular histogram of results is consistent with the errors that you'd expect to see from that hardware. But if you don't know the error characteristics of the hardware, how do you know which errors are attributable to the noise in the hardware, which are attributable to the noise in the algorithm, and what might just be a programming bug. And for that, I think it requires a certain depth of understanding of your particular quantum algorithm, and a lot of exercise and execution on simulators that are available to you to try to explore that quantum algorithm. I think once you get into the realm of algorithms that are too big to simulate on current hardware, then you've got a really challenging question to answer. Hopefully, evaluating the correctness of an answer is simpler than the process needed to generate the answer. Otherwise, you have identified a very difficult quantum algorithm to evaluate. But I think that's an active area of research and definitely something that is a little bit outside of my ken.
All right, thank you, though. So another question is, so you showed IonQ and Honeywell hardware platforms, but is there any other hardware platforms that is available through Azure? So
we have announced partnerships with other providers, for example, QCI, but currently those are not available as part of our public preview. So for now, the hardware providers that are available in public preview are IonQ and Honeywell, but we certainly hope and expect to expand that to more providers in the coming months and years.
Perfect. So that was the end of the questions.
Great. So I did want to take a look at another algorithm so that we could see an example of how these tools allow you to perform certain kinds of execution. So let's take a look at a simple teleport algorithm. Now, this one is much smaller. We can see the whole thing on screen here, and I can actually walk through this one. You know, I am not a quantum expert, but I am familiar with programming in Q# from having worked on the language. So I can discuss this one in a little bit more detail. Here we can see it is just the kind of basic example of teleport that you would expect to see, kind of the textbook example, where we take 2 qubits, we establish a bell pair using H and C naught. Then we have our input qubit, where based on an input Boolean that was provided, we decide whether or not to set that qubit into the 0 state or the 1 state, where 1 corresponds to an input of true. And then we perform the teleport through the bell pair by first doing a C naught with our input qubit and one of the qubits in the bell pair, then Hadamard, and then perform some measurements on that first qubit in the bell pair in order to get the classical information that would be necessary to understand which corrections to do to the second half of the bell pair in order to read out the teleported value. Now, what's interesting about this is that it demonstrates a feature of the Q# language that we weren't using in Grover. Here we are actually doing an if statement based on a measurement of a qubit. And that if statement is determining which operations we perform, which quantum operations we perform on another qubit. Now, in order to do this at runtime, you know, in a simulator, obviously we can just perform the measurement, but at runtime on quantum hardware, it requires specific features that may or may not be available on the target hardware. As an aside, our goal with Q# was not to design something that is specific to the capabilities of today's NISQ systems, but really to explore the full problem space of quantum programming, even if certain constructs may not be executable on today's hardware. Now, in this case, we do have some hardware that can execute this, which is the Honeywell hardware. And you can see in my project file, I've specified that I'm targeting a Honeywell execution target. So if I bring up my command line here, and let's go out into the teleport sample. And I say .NET build. This will build just fine, indicating that as best as we can tell, this program is ready for execution on a Honeywell target. Now, different targets, as I mentioned, have different capabilities, and some of those capabilities are part of the preparations and transformations that the compiler will do on the code as part of getting it ready to execute on that particular hardware. So if I take the IonQ QPU and insert that here, I do get immediate feedback from doing the build that the particular execution target that I have chosen doesn't have the right quantum processor capabilities to be able to satisfy this particular program. Here we see a nice error message giving us that feedback. So this is one of the ways where we are trying to build these tools to help, guide developers to what sorts of programs they're able to execute on different targets. So let me go ahead and put that back and rebuild. And we can see that build is successful, indicating that I'm ready to execute a program that has mid-circuit measurement. Now, like before, if I do .NET run and I give it the input of true, because the teleport algorithm is very simple and very kind of well known, on an ideal simulator, we're going to see that return the output of 1 for the input true 100% of the time. If I give it the input false, I'm going to get the output 0 100% of the time. Again, that is because there is no noise in this simulator. Now, if I execute on the Honeywell API validator, which I can do using a similar quantum job submit command. Here you can see my target that I've specified has this additional -API val at the end of it. I've given it the name teleport, and I'm going to give it the input true. So I am going to, once this actually returns, get out a job ID here. And checking the results of this job ID, we see something actually pretty unexpected here. We got 0 100% of the time. Now, this can occasionally cause some confusion. And this is the difference between an API validator versus a simulator. Where IonQ exposes a simulator endpoint, the Honeywell endpoint here is for the purpose of verifying that a given program is valid, but it does not actually perform any simulation or execution of that program. So, we've had some folks get a little bit confused by this, but this is completely expected. An output of 0 with no failure message, no error codes returned means that as far as the API validator is concerned, this program is valid, and it just always returns 0 as the output here. So instead, what we'd like to do is we'd like to execute this against the hardware. And as you saw before, what I can do is just change which target I'm executing against, remove the API val here so that I'm executing against the Honeywell hardware target. And that will queue this job for execution against their system. Now, I think that their system might not actually be online right now. So this job is going to wait in the queue until it is actually ready for execution. You can submit a number of jobs, let them queue, and when the provider is ready and the hardware is available and calibrated, they'll pull those jobs from the queue, execute them, and you'll see those jobs marked as successful in either in the job output here or in the workspace. So if I refresh this workspace, we can see the successful execution against the API validator, and it's waiting on execution for the teleport algorithm on their hardware. Now, like any good cooking show will teach you, it's a good idea to have already cooked one before. So I did previously execute this teleport algorithm against the Honeywell hardware. So we can copy this ID. And just to show what it looks like, I can go ahead and download the job output from the workspace here. And if I open that file, we can see the histogram, the same JSON histogram that we get when we query from the command line, showing the output. And here we can see 97% of our executions resulted in 1, and about 3% resulted in 0. Not not a perfect ideal, but that's actually really good feedback to show us that we did actual execution against hardware. Just to show it one more time here, Azure Quantum Job Output, give it that same ID. And we can see the same output visualized as a table here. 97% of the teleports were successful in that they returned the result that we'd expect given the algorithm. So when you're using these tools, it can be helpful to know what some of the other commands are for kind of exploring the available capabilities that we have. So one of the things that's worth showing here is that I can list all of the jobs that I have. And by default, this will list them in a JSON format, which is nice and programmable. I can write scripts to parse this and look for particular information. This output is essentially just the raw JSON output of the same view that you see here from the quantum workspace. But that gives me some tools and some additional data that I can use to understand, how this executed. For example, seeing the number of shots that were requested for a particular execution, things like what the input data format were, which is just the format that we use when communicating with the hardware partners, and getting information about where the output blob, where this file that I downloaded is stored on Azure, so that you can use other Azure tools to be able to automatically and programmatically download data from your jobs. And so what this shows is that by combining the Q# programming language, local simulation through the QDK, and the partner execution that's available through Azure Quantum, you can actually explore what the particular performance of a given quantum program is like across different hardware partners, and through different shot counts and with different inputs, all by utilizing the tools that are available today through the Azure Quantum Preview. With that, I did want to see, are there any other questions at this point, or?
Yes, there are 2 questions actually. So the first one is, for example, with IBM, we can simulate the noise models of the devices. Is it possible with these 2 hardware platforms as well?
Right. So right now there isn't a solution available for that, though I know that is feedback that we have gotten and that our hardware partners have gotten, is that it is valuable to have either simulators available that model the noise of the particular hardware, or a way that you can query for recent calibration information that give you output so that you can configure your own noisy simulators to model that particular hardware. Now, that's not something that is available today, but it is something that we are working on and that our partners are working on, trying to find the right solution and the right way to expose that. One of the things that does make that a little bit challenging is that API might be something that you need to query often, given that these machines are constantly being calibrated, periodically taken offline for maintenance, and then brought back online with different noise characteristics as the hardware is updated. And so that is kind of one of the challenges of NISQ hardware, is maintaining a current active noise model. And so that's something that we are hoping to provide in the future, but is not currently available with the preview of Azure Quantum.
All right. So thank you. And the second question is, so the attendee is asking, so I have heard that 0 is preferred for quantum computers in a program if one knows that there are more ones than zeros. Whole code can be inverted, thus making it more stable to errors. Are there such inversion commands or even check for Azure Q?
That's a good question. So I think that's one of the things that you can look at in terms of the flexibility that the Q# programming language provides. Let me see if I can do, how would I give an example of that here? It doesn't really, I'll just write some code here to demonstrate it, but it won't actually tie into the teleport algorithm. But let's say a pretty frequent pattern that you'll see in certain quantum algorithms is to perform a particular operation on a qubit, and then to prepare a state, then do the actual kind of body of the operation that you'd like to perform, and then do the adjoint of a of the preparation in order to get the qubit back into kind of its original basis or its original state. And this is such a common pattern in quantum algorithm that it's something that we have a shorthand for in Q#. So you can actually use what we call a within apply block. So within X, apply H. And what this will do is automatically the simulator or hardware execution will know that this pattern means for everything that's in the body of the within, you perform that initially, then execute the body of the apply block, and then do the adjoint of everything that's in the within block. And so this is equivalent to the code that I wrote previously. Now, part of what makes this convenient is, it's not that much shorter if you're just looking at a preparation that does something like an X, but you can actually define operations. So I'll just put an operation here. Let's call it foo, that takes a qubit of type qubit. And I say that it is unit, and I identify this as an adjointable operation. Then everything that I perform in here needs to also be adjointable, such that then what I can actually do is put foo in here. And now across multiple user-defined operations, the compiler will know that what we need to do is for the entire body of the foo operation, whatever operations are performed in there, the adjoint of those need to be performed as part of exiting this within apply construct. So that doesn't perhaps directly answer your question, but perhaps it does show you some of the tools and the features available in the programming language that would allow you to include that kind of logic in the program as you write it. And that's sort of what I mean when I describe Q# as not really a language for just describing a circuit, but we provide kind of more fully fledged features that allow you to write the program. You're describing the logic of the algorithm, and then between the compiler and the translators that make it possible to execute this on quantum hardware, that will eventually become the sequence of instructions necessary to perform that execution on today's hardware. So hopefully that answered the question. And again, when it comes to details of kind of features of the Q# language, I definitely encourage you to check out the talks we have later in the week that go into more details about using Q# and the QDK.
All right, thank you. That was all of the questions so far.
Great. So one other thing that I did want to show off is kind of the opposite of the example that I did earlier, where I showed that teleport was not compatible with IonQ, even though it was compatible with Honeywell. If you have a program that could be compatible with either, for example, the Grover program that we chose, I can actually change this. Let me copy it from here so that it is compiled for the Honeywell target. And build it for Honeywell and see that it succeeds, which, this is a very nice advantage of having some of this target specific knowledge built into the compiler and the translators, is that without needing to make any changes to the actual body of my program, without needing to adjust which qubits are used or which commands I'm utilizing and how those commands are expressed, I can take this same quantum program, the same expression of the Grover algorithm, and run it against either IonQ or Honeywell. And in fact, even with this set to IonQ, let me rebuild it to show that it is currently built for IonQ. If I take this program and I run it through the Azure job, AZ Quantum job submit, like what we did before, Let me just select 2 qubits and target it at the Honeywell hardware. What the AZCLI is doing here when we say quantum job submit, it notices that the target that I'm requesting execution for is not exactly the same as the execution target that is selected in the project file. And so it will actually do the correct compilation with the right steps for me automatically as part of preparing that program for submission and queuing it on the Honeywell hardware. So here we can see I've taken that same Grover program, and in this case, without needing to make any changes to either the project file or the actual content of the Q#, I've prepared it for execution and submitted it for execution on Honeywell. And so as hardware providers advance and as the field of quantum computing advances and more of these hardware partners expand their capabilities or identify particular specialties of their hardware, we are trying to build a set of tools that gets us toward this ideal vision of writing a quantum program that describes your program execution and then being able to execute that across a wide array of hardware partners. One of the things that we're doing in order to enable that is Microsoft has been collaborating with the quantum community on developing what we call QIR, the Quantum Intermediate Representation. Now, this is a feature, like so many of these things, that is still in preview. But if I go to the Q# language repo, you can see that we have here a section with specifications, and there's one on QIR. So this quantum intermediate representation is actually it's not a completely independent or unique and new intermediate representation, but rather it's a specification for a way to use LLVM IR in order to describe quantum programs. And it does this without requiring any extensions on or addendums to LLVM, but rather just uses existing LLVM IR and patterns within that to describe a quantum program. And part of our long-term vision for how QIR could be used is that it can be a common intermediate representation for a number of different front-end languages. So it is not Q# specific. And it can be interpreted and compiled into target-specific representations across a number of different targets. So really kind of the true goal of an intermediate representation. And we have some projects today that are already using QIR, such as projects with Oak Ridge National Laboratories or Pacific Northwest National Laboratories that are making use of QIR. And we're actively working with our hardware partners to bring on QIR as a format that they actually adopt, as well as engaging with the community on projects that take front-end languages besides Q# and compile those into QIR. So we really do see this as a strong path forward for the industry to kind of start unifying behind a common intermediate representation. And we see a lot of value in using an existing IR like LLVM because of the strength of tools that are surrounding it, like Clang, that allow you to do compilation of LLVM IR and certain optimization passes. You can already use existing optimization passes with QIR, or this opens the door for people to author new optimization passes that are quantum aware, that may take into account the patterns established by QIR in order to perform quantum specific optimizations to code. So, this is, I think, kind of the next phase of the goals of Azure Quantum, this goals of execution across a number of different hardware partners and using a number of different front ends, such that I would definitely encourage checking it out, reading up on the specification. We have some great blog posts from some members of the Azure Quantum team describing QIR and its goals, as well as some posts describing the ongoing projects that I mentioned, including the collaborations with PNNL and ORNL using QIR. With that, that's actually everything that I had prepared. I'm happy to stick around and answer any additional questions and go into more detail either about the language, QIR, or the Azure Quantum tools. Happy to answer any questions you might have.
All right, thank you very much. Actually, it was very informative for me as well. I hope that's the same for the attendees as well. So one question is actually, I guess you covered this in the last part of your talk, but what features are in plans to be rolled out in Azure's quantum platform in the near future?
Yes, so I can't go into too much detail about things that we haven't announced yet, but there is, of course, ongoing and active development around Azure Quantum. A lot of it is actually related to QIR, as I mentioned before, kind of trying to pull that in as a common intermediate representation across multiple endpoints and multiple targets. But one of the big things that we see as the draw for Azure Quantum is our existing QIO solvers, which I know wasn't the topic of today, but definitely something that I would encourage you to check out, as well as bringing online more hardware partners such that you can take the Q# code that you've already written and try that against different kinds of hardware that's based on different underlying technologies, partners that have different kinds of support or different features or profiles that are available for their hardware that really allow you then to use Q# and Azure Quantum as kind of the common front end to experiment with a given algorithm and really explore the problem space of quantum computing across all of those different possible execution environments. So the main goal really is bringing online more partners and giving users more opportunity to try execution in different environments. And look for exciting announcements in the coming months about what new availability there will be, both for private preview and, of course, eventually for public preview. We're hard at work bringing online as many of those things as we can soon.
Yeah, that's great news.
Yeah.
So I don't see any other questions right now. I guess I will thank you again, and thanks to all of the speakers and attendees for the great questions. So we will take an half an hour break right now, and the next session is going to start at 4 p.m. with IBM Quantum Programming Lab. So hope to see you all in that session.
Thanks, everyone.
All right.
Nice talking to you today.
Thank you.